Hello wonderful person, this is Anton, and in today's video I'm going to teach you a little bit more about the structure or the anatomy of a black hole using video games. Today you're going to learn a little bit more about black holes, and we're going to use both Space Engine and Universe Sandbox Square to learn about these awesome, unusual objects. Now, we're going to be actually talking about the structure of black holes, but before we do this, let's actually take a look at this simulation that's called Black Hole and the Sun that will kind of actually show us how the accretion disk is made around this beautiful tiny black hole right here. So there's our sun basically being shredded by the black hole, and there it is creating the beautiful accretion disk. So first of all, let's talk a little bit about what we see here. This black hole looks like a typical black hole in Universe Sandbox Square. It is not a very realistic representation of a black hole though. All of the black holes here are basically just this. They're literally black holes with a bit of a lens effect around them. That's not exactly what we're going to be creating here. We're going to be trying to create a very realistic representation of this unusual space phenomenon that Einstein didn't really think existed. But let's just start by creating a relatively realistic black hole using Universe Sandbox and some of the bugs in the game. So we're going to go under planets here, and let's just choose any gas giant. I usually just pick Jupiter, and go under the settings here and change the actual mass of Jupiter to about 120 or maybe 200 Jupiters. This will create a red dwarf, but it's going to look kind of unusual. It's actually almost looks like a black dwarf, but it's basically a very small star. We're going to do this again, but this time we're going to click on the sun value here, and let's just change this to about 1.5 suns, and then reset this, and it will create these beautiful jets around it. So this is kind of a bug in the game that is necessary to create a realistic looking black hole here. The last step here is to decrease the size of this object to, let's just say, about 2 kilometers. And boom, and there is our beautiful black hole that now has these relativistic jets that are projected from both directions. This is absolutely necessary for us to essentially create a realistic looking black hole. So now I'm also going to give this black hole a little bit more mass just so I can actually place objects around it. And let's maybe stop its velocity because it's moving around a little bit too much. And so now we're going to try to create the second part of this black hole. We're going to create the accretion disk. Let's maybe place a star or two around it and see what happens here. All right, so there's the beginning of our accretion disk. I should have done this a little bit slower, actually. This was a little bit too fast. Let's place another sun right here. And this will start creating the accretion disk around the black hole. And to create a relatively realistic looking accretion disk, we actually have to shred quite a lot of stars. We actually have to basically do this for a few minutes. But as you keep doing this, you'll notice that many of these stars will start acquiring mass. So you have to kind of erase them just so that they don't go supernova. I'm going to place a few more here, just so we can create an accretion disk closer to the black hole as well. And I think this is actually kind of enough for now. So there is our accretion disk orbiting around the black hole, and there is our particle jets protruding from both sides of this black hole. Now this right here is a lot more realistic already. So every black hole has the accretion disk formed by all of the matter that essentially falls into it and starts kind of orbiting around it. All of the black holes, or most of the black holes, especially the ones that actually have stuff falling into them, will have these two relativistic jets coming out from basically top and bottom. And we still don't really know why exactly this is happening and how exactly they're formed, but we know that basically all black holes have them. And when a black hole is very, very powerful, meaning that it shreds a lot of matter and it just so happens to project its jet directly into us, this is what we would call a quasar, or in this case, a blazar if it's a little bit off. These are some of the brightest objects in our universe, and we actually see them from as far away as basically the limit of, or the border of the universe. So that's the first two parts that I wanted to cover, the relativistic jets and the accretion disk. Now let's zoom in here a little bit and talk about the other two parts, essentially the two parts that all black holes possess as well. One of them is the singularity, and it's right in the middle of this black hole. This is essentially a point where all of the mass has actually been condensed into a tiny, tiny, tiny point, infinitely small point that essentially curved and warped the space around it so much that it created a black hole. Now, It has close to infinite density, and it's essentially almost zero volume, but not quite. And this particular point is something that we can't really explain using modern physics. As a matter of fact, everything inside of the black hole doesn't obey modern physics anymore. It's the only physics we know that kind of covers a little bit of what's going on inside the black hole is the quantum physics, and even that is not really good at explaining what exactly is going on the inside. Now, right around the singularity, right here, this is what we call the event horizon. This is basically the area around the black hole where no light can escape. Essentially, at this point right here, the escape velocity you need to have is speed of light. And since nothing can move faster than the speed of light, this essentially becomes black. And this is why we call it a black hole. So technically, it's not really black, because it does have a bit of radiation coming off it, known as Hawking radiation, that is formed through another quantum mechanic concept known as quantum tunneling. But we're not going to cover this just yet. This will be a special video sometime in the future. But this particular area is also known as the Schwarzschild radius, and it actually can be measured using a very simple formula that you see on the screen right now. And this radius is basically calculated using this formula, and this is where the event horizon starts. Now, a smaller black hole like the one you see here, or even a much smaller one of just one mass of the sun that I'm going to place right here, will have its Schwarzschild radius or its event horizon at a very small, short location here. And as a matter of fact, the radius here is just 3 kilometers. This larger black hole that's approximately 10,000 masses of sun is just a little bit larger than our planet Earth. So it's just a little bit larger in terms of its event horizon. So basically, these are not very large. But the larger the black hole, the larger its Schwarzschild radius. And so the black hole in the center of our own galaxy, Sagittarius A star, has a very large Schwarzschild radius of close to about 1 astronomical unit, which is basically the distance of Earth to the Sun. So essentially, if we were to place this black hole in the middle of our solar system, it would swallow everything up to the Earth. And we're going to do this at the end of the video. But let's actually just keep talking about different structures. So this is the event horizon, the accretion disk. You have the large jets of gas, very highly energetic particles coming out from the top and the bottom. We have the singularity in the center. And of course, the event horizon is explained using the Schwarzschild radius. And there's actually one more area around the black hole that most people don't realize exists. Now, to show you the next concept, I'm actually going to create a new black hole, and we're going to use our own Sagittarius A star here. And I'm going to explain to you something known as the photon sphere. Now, this actually does have a photon sphere, and it's inside here, but I can't really place an object there, so it would be impossible for us to see. If I were to place another smaller black hole in orbit around this black hole, it would orbit at a speed of about 180 to 200,000 kilometers per second. Not exactly the speed of light, but very close to it. So I'm going to make Sagittarius A star about 10 times bigger. So now let's try this again. We're going to place a black hole right here, and maybe right here, and maybe right here, and maybe a few more on the outskirts here. And notice how this one here has the velocity of 1.5 speed of light. Now that's impossible. It's actually going to fall into the black hole. So we need to change this to 1 speed of light. We're going to go and do this for all of them because nothing can move faster than speed of light. So all of these other black holes will be actually orbiting at the maximum speed, which is going to be just under the speed of light, except of course for one right around here that we're going to name the photon sphere. This particular black hole is orbiting at the velocity of light, or the speed of light, 1 speed of light. And this is essentially where we have this theoretical concept of photon sphere that we're hoping one day we'll be able to see using more powerful telescopes. But essentially what this area represents is the area where all of the light that ever came into this black hole and all of the photons that came here that basically got stuck and now orbits around this black hole. Now this is actually represented really beautifully in Space Engine that you can kind of see on the screen right now. But here it's going to be very difficult to represent because we're not going to be able to create this type of an environment. Other black holes that are orbiting within this region are in the area known as the unstable orbit region. Now, everything here, doesn't matter what it is, will never be able to maintain a stable orbit. So all of these black holes will actually fall into the supermassive black hole right there, and they'll basically disappear forever because their speed will never be able to cross the speed of light. All of them will actually get absorbed by the black hole, so nothing can survive this area. Everything outside of it is known as the innermost circular stable orbit region, and here you can actually still have masses and objects. Like, for example, we're just going to place a bunch of stars, or specifically our own sun, in orbit around this black hole, just to give an idea that you can still have a bunch of mass orbiting right there. And this is essentially what the accretion disk is. It's formed by all of this mass orbiting around the supermassive black hole, and it creates this unusual, beautiful effect. And of course, the accretion disk itself, that then is responsible for creating the relativistic jets as well. So whatever mass falls into this region and gets absorbed by the supermassive black hole disappears forever and basically creates the relativistic jets. Now, there's one more thing I haven't covered in this video, and I think I'm not going to cover it just yet because it's a very complex concept and it's something I wanted to talk about separately, and this is a concept of the ergosphere. Now, ergosphere refers to the idea of a spinning black hole, a black hole that spins really fast and creates a very unusual effect around it that sort of looks like this. It's basically an egg-shaped effect of warped space-time. Now, this is a cool concept that we think maybe one day when we're super advanced, we'll be able to use to harness energy, but I don't want to talk about this just yet because I've already covered all of the necessary areas and parts of a typical black hole. So you know a little bit about singularity, you know a little bit about the event horizon, the Schwarzschild radius, the relativistic jets that are unfortunately not here anymore because I had to create a new black hole. You also know about the accretion disk, the innermost circular stable orbit, and the photon sphere that's somewhere right around here. And I think to start this simulation, what we're going to do is we're going to first create the central region where the central black hole is located. Now, I've talked about what this might look like in one of the previous videos, but basically here we have the central black hole that's about 4.3 million masses of the sun. And then we're going to basically place a bunch of random stars in orbit around it. Now, these actually do have very specific names. There's a few stars that we've discussed in that video I did previously where we recreated the system. But here, just for the sakes of time, I'm going to just randomly create a few of them just so that we actually have them in orbit. As you can see, some of them are already falling apart because of the tidal effects, but that's okay. We're also going to place a few smaller black holes because we've recently discovered that there is up to about 10,000 smaller black holes orbiting around Sagittarius A star in a relatively close proximity of it. And so we're just going to place a few just so they're located somewhere there. And there you go. So this is the central region of our galaxy. We're not going to try to put too much stuff just because we don't want the game to be too slow. And now let's go into the stars here and choose our sun. And what we're going to do is we're going to assume that maybe sometime in the future, millions of years in the future, by some unknown accident, our sun gets nudged from its actual orbit and basically approaches relatively close to the central black hole. Now, it's not impossible. It's actually something that may occur if there is enough mass that sort of influences the orbit of our sun. And because Sun has already orbited Sagittarius A star approximately 25 times in the last few billion years, basically here, maybe, just maybe, one day it will actually approach this relatively close. But let's find out what happens if it actually basically plunges through this central region right here, relatively close to the black hole, but not exactly into it. And basically, let's discover what happens to our solar system and specifically our planet Earth. So I'm going to launch the sun, or actually I'm going to launch the whole system with all of the planets and all of the moons, everything coming toward the central region, starting now. So there it is. There is our sun, there is the Neptune and other planets, and we can even take a look at the orbits here. And as you can see, almost right away, the orbits get really stretched. Now, maybe I should have done this from a slightly further away distance. Let's actually do this again. I'm going to erase this and come a little bit farther away and do this again from a farther away distance, just so that at least we have some of the stuff, such as orbits, slightly more visible. So here, the orbits, due to the tidal effects of the black hole, get stretched almost right away. Now I'm actually going to erase some of the moons that are here, because they're going to slow down my game dramatically. So all of the moons of Jupiter and all of the other gas giants are basically going to be erased from this simulation, just for the sakes of maintaining speed that I need to make this simulation manageable. So we're going to just go in here, select all of them at once, and then go in the middle and click on the planet, so that only the planet remains. But I think we're going to keep our own moon, just because we want to see how its orbit changes as well. So let's actually just remove all of this and see if we can run the simulation a little bit, just to see what starts happening. So because we're still relatively close to the sun, nothing really changes on Earth. It's still going to be very habitable, there's still going to be good enough temperature, and the sun is still somewhere out there. But because if you actually look at this from the top here, because sun is slightly closer to the black hole than Earth is, it's actually going to start accelerating toward the black hole a lot faster. Mars is even closer, so it's going to accelerate even faster. And what this means is that sun is actually going to start moving away from Earth. Actually, all of these planets will start approaching the central black hole at a different velocity. And this is due to the different strengths of the gravitational pull at different points. So right here and right here, the effects are dramatically different. Earth receives a lot less gravitational effect than the sun does. So if I actually zoom into Earth again, and I go under motion here, you'll see that the distance to the star is increasing really fast. We're basically moving away from the star at a ridiculously high speed. We're already at a distance more farther away than Mars is from the sun, and it just keeps increasing, because sun is essentially being attracted to the central black hole really quickly. And here, this is also sort of affecting the actual shape of our planet. So the pull right here is a lot stronger than the pull right here. So this means that our Earth will start becoming stretched. It's going to become sort of elongated and become egg-shaped, and all of this can actually be analyzed using this value right here, known as tidal stress magnitude. Now, as soon as this value becomes more than 1, our Earth will no longer be able to maintain its shape and start losing its consistency. It's actually going to start becoming basically an asteroid belt. It's going to fall apart into little pieces. But we're going to run this for, I guess, a few years, until these planets and, of course, our sun approach the central black hole. But essentially, even within a few days, the entire solar system is completely destroyed. It's basically isolated, and all of these planets become attracted to the central black hole, and their orbits are now completely different. And because the sun is so far away from our planet, we now get a lot different climate here. Specifically, basically everything becomes really cold. The snow starts advancing into Africa. It basically means that we now have reached a new ice age, and this will actually last for quite a long time, until we reach the actual central part of the central black hole, because there are other stars there that might be able to warm us up. But until we get there, we're going to be very cold, because our sun is actually flying away from us, and we can find out at what speed. So if I were to go down here under motion, I would see that my current velocity is 42.1 kilometers per second. I guess it's already 42.2. If I were to look at the sun, its velocity is at 264 kilometers per second. It's already moving a lot faster, and it's also accelerating a lot faster than our Earth. So it's going to move away farther and farther away from us, and this means that our heat source is slowly disappearing, and the entire planet is soon going to be covered completely in ice. Now, if we're still present on this planet, I guess we might have to start building underground cities with essentially heat sources somewhere underneath on the inside. But you know what? I'm not even sure if we'll be alive by then, because this is millions of years in the future, when sun one day makes it to the central region of the galaxy, or possibly even billions of years in the future. For all we know, human race by then does not exist. Now I'm going to accelerate this a little bit just so that we can advance time, and we're going to approach Sagittarius A star a little bit closer. As you can see, all of the planets are now basically directly dependent on it. They're not dependent on the sun anymore, and even the sun is basically being dragged toward it very, very, very fast. I'm not sure if anything will collide with it, with the central black hole, but it's very likely that at least a few of these planets will actually get completely eliminated and annihilated. And it's been a year now since I started the simulation, and we're still kind of far away from the central region, but let's just take a look at what's happening with, well, I guess let's start with some of the other planets. And I guess here, Jupiter and other gas giants will not really look that different, but I'm kind of curious about Mars, Venus, and also Earth. So starting with Mars, which seems to be a little bit more red than usual actually, not sure why, but possibly because of the other stars. And what we can see is that the temperature has decreased just a little bit. It's moving toward the black hole at a velocity of about 470 kilometers per second, but other than that, it seems to be just kind of what it used to be, very similar to what it was like before. How about Venus? Has Venus actually cooled down a little bit? And the answer to that is yes, it's actually surprisingly very cool. I don't know how it got so cool, but I guess it's because the sun has disappeared from its vicinity and it's now been sort of losing a lot of the temperature and releasing a lot of the heat that used to be on the inside into the outer space. So now Venus may actually even be terraformable because it is kind of far away enough from the sun and doesn't receive as much temperature. Which also means that because Earth has completely basically frozen over, this is Earth, we might need to move to Venus because it might be a little bit, oh actually no, never mind, this is still a little bit hotter than Venus. But yeah, Venus might be a potential target for our new existence, and we might need to move there if this ever happens. Alright, so let's run this a little bit more, but actually before I start running the simulation again at a higher velocity, I just wanted to mention that because this is millions of years in the future, all of the continents will look very different as well. The plate tectonics will actually move all of these continents around, so the face of Earth will be very different from what you see right here. This is not very realistic, but since we don't have an ability to move the plates in this game, we might have to just ignore this fact. Alright, let's skip another year and see what happens. Now, after 2 years, Sun is actually significantly farther away from everything in our solar system, and as you can see, it's moving a lot faster than the other planets. You can kind of see it better if I were to zoom in on the Sun. And from this angle right here, you may notice that the other planets are basically dragging behind it, where Sun is moving really, really fast toward the central region. So let's wait until all of these objects actually make it to the central black hole. And after this, we'll see what actually happens to each one of them, but specifically our planet Earth, which is somewhere in the back behind everyone else. Now, after about 3 years, you can kind of see we're approaching the central region relatively quickly. I'm going to take a look at the velocity in a second, but it's getting closer and closer to us. So let's look at the velocity of the Sun here, and it's basically over 3,600 kilometers per second, which is like about 100th, or I guess 1/80th of the speed of light. And it is actually increasing really fast, so you might even reach higher velocity. So the Sun is going to be the first object to approach the central black hole and the central region, and it might even collide with the black hole. So let's see if it actually does happen. I've run this simulation previously, and Sun does seem to disappear somewhere. It possibly gets a collision with the Sagittarius A star. But some of the planets don't. Some of the planets actually do survive. So we'll see what happens here in a few more months. Now from this angle, this looks really, really cool. I'm going to slow this down a little bit. You get these really beautiful stars. Oh, no, there we go. It actually exploded. You got these really beautiful stars, and it's almost like fireflies orbiting around the central black hole. And so what happened to the Sun is that it actually did sort of scratch the surface of the event horizon and lost a lot of its mass, but it still is around. It's only about 25% of its original mass, but it survived. And now this actually does happen in real life, where some stars sort of graze the central or a supermassive black hole sometimes, and they release a lot of these materials, And some of these materials get into the accretion disk of the central massive black hole and then are released through these two energetic particle jets that are usually pointing away in two separate directions, which is often how various quasars and blazars are created. But anyway, let's go to the first planet that is going to come close to the central region here. And I think the first planet is going to be Mercury because it was the closest to the Sun. And similar to the Sun previously, the velocity here is suddenly dramatically jumping up to about 20,000 kilometers per second. But I'm going to actually go into this setting right here because I want to see the tidal effect. So you can see the tidal stress magnitude right here. And as soon as this reaches 1, it's very likely that Mercury is going to start falling apart into little pieces. And let's see if this actually happens. So we're going to wait a little bit more. And as we're getting closer and closer, you'll notice that things start increasing quite dramatically. So tidal stress magnitude is increasing. That means that Mercury is now going to get really, really stretched. It's going to basically kind of get spaghettified, but not to the extreme effects of what you would expect from a smaller black hole. And also because there are so many stars here, you will also get a lot of various illumination from various stars, and there you go. So that was actually Mercury passing relatively close to the central black hole. It kind of grazed it as well and is now moving away from it. So it basically lost some of its mass and is moving away at the speed of about 36,000 kilometers per second. Now I'm going to try to do this again, but this time a little bit slower with the next planet here, which I guess is going to be the gas giant Neptune. Now this might be actually very interesting, so let's see what happens here. And interestingly, the surface of Neptune is extremely bright right now. The temperature is actually increasing dramatically as well. It's going really fast up, but it's mostly because of the tidal effect. So it's basically being stretched to the point where the tidal heating effects are ridiculously high. And it's really because of all of this really high gravity that's essentially produced by the central black hole that's right there. You can actually even see it from here. Now, what is the distance to the central black hole? And it says here that the distance is just over 10 astronomical units, which is kind of realistic in terms of the distance to the Sun from Neptune. And it's coming closer and closer. We're going to slow down in a second just so we can see what actually happens when it gets really close to the central black hole here. And right around now, when the tidal stress magnitude gets to about 1, we'll see how Neptune might actually fall into little pieces. Or it might actually, yeah, it might actually collide with the central black hole because it looks like it's going straight for it. So there we go. The tidal magnitude is at 30. You'll actually see all of this falling apart in a few seconds, and then it's probably going to combine into the central supermassive black hole. And just to give you an idea of how fast we're actually moving, this is going to be in real time. And we're actually moving at about half of the speed of light right now. Very fast. You can see the central black hole right in front of you. This is a huge object right here. This is the event horizon of the central massive black hole. And Neptune is unfortunately going to be falling apart into little pieces. So there's a lot of fragments coming off the surface, and that's because of various forces acting on various parts of the Neptune here, and essentially spaghettifying it and stretching it and making it suffer quite dramatically. Alright, so let's accelerate this about 5 times and see what actually happens to poor Neptune that's possibly going to basically smack right in the middle of this object. And there we go. Neptune has been swallowed by the black hole. Now, whether this happens to Earth or not, I'm not actually sure, but let's find out by waiting for, I guess, a few more years and just kind of seeing what happens to these other planets. As you can see, Mercury has already left. It became what's known as a rogue planet, basically a planet without any star. Our Sun became actually a red dwarf. This is a type of a star that will live for a very long time, possibly even trillions of years. And the other planets might also become rogue planets or combine with Sagittarius A star. And also our moon has left us for some unknown reason. And there goes the Saturn. It also became a rogue planet, moving at a very high velocity, half of the speed of light away from the system. And something completely different happened to Jupiter. It actually turned into a very, very tiny rock that's only about 137 meters in radius. I think the central black hole actually swallowed most of its mass. So now it's this smoking rock in the middle of space, which is very, very unusual and very unexpected. Okay, so how about Earth? And Earth seems to be approaching the Sagittarius A star at a slight angle here, so it might still get influenced by these other bodies, but it's very likely that it might be able to survive all of this ordeal and not be destroyed like the other planets, or might even stay in orbit around Sagittarius A. So let's actually slow down the time here and go through this simulation in a little bit more detail as our beautiful planet approaches this somewhat scary and dangerous region. First of all, we're still living in Ice Age. It's been about 4 years and something like 2 months. We're basically living on a nice planet, ice ball, that has no source of energy. But suddenly there's all these other stars in the region that might start illuminating our planet and create a bit of sort of light and also a bit of energy for us. So maybe the humanity that used to live under this ice sheet will actually come out and get to witness this incredible view of various stars and various black holes orbiting around the central region. So basically, they might see this incredible view of the dance of the fireflies, as I call it. And if I actually stand on the surface of our planet by pressing C button, you can kind of see what they might even observe in the sky. These stars moving at very, very fast velocity. Sagittarius A is right there. You can kind of even see the outline of it. And all of this looks absolutely, absolutely incredible. So this is what we might see if we actually approach the central region. And as we're approaching the central black hole, this is what our beautiful planet now looks like. It's essentially one big snowball illuminated by many different stars around it. So basically we have daylight pretty much everywhere, but the temperature here is still pretty cold because it hasn't really spent enough time being warmed up by various stars. And where exactly is the central black hole? Well, it's actually right there. This is how close we are to it. And basically here, at this point, this is where the tidal effects might be strong enough for our planet to start losing materials. We're going to go into tidal stress here. You can see it's at almost at 0.1, and it's still increasing. If it ever reaches 1, this is when we start losing things. But right now, what our planet is experiencing is ridiculously strong tsunamis, a lot of earthquakes, and a lot of volcanoes going off everywhere because the strength of this tidal force is ridiculously strong. On top of that, we're also moving really, really fast right now. Our actual speed is 60,000 kilometers per second. This is when you get to witness or start noticing relativistic effects. Basically, if anyone was outside of our planet Earth, they would see us moving in slow motion, where it would actually move slightly slower than usual. So basically, we're now living in a time machine. We're going into the future, and a lot of the things on our planet are slowed down. But let's actually see if anything gets ripped apart by the tidal forces, which are now at about 0.55. This is really, really, really strong. And it only took a few moments for us to get to over 1 magnitude of tidal stress. Now, nothing is flying off the planet just yet, but this white, beautiful ball that's basically illuminated by other stars might actually start feeling the stress really soon. I would not be surprised if this is when we start losing our rocks and our ice sheets, and basically people that might accidentally travel to the surface of the planet. Although surprisingly, nothing really flew away, nothing really happened. I think it's maybe because we did this a little bit too fast, but looks like our planet survived and is going to come out of this situation completely unharmed. Although the climate here is still pretty cold, the actual temperature is very, very low, and we're still living in the ice ball Earth. Now at this point, I think we're actually flying away from Sagittarius A star, and I think we might actually be in orbit around it. Oh, that's right. We have achieved an orbit, a very, very elliptical orbit around Sagittarius A star, which means that our planet will now stay here forever. Or I guess for as long as something doesn't disturb this orbit or destroys our planet. Now let's see what happens after a few more years. We're going to run the simulation a little bit longer and discover what happens to both the surface temperature and also the actual shape of our planet. And looks like something happened to our moon. Our moon traveled a little bit too close to Sagittarius A and has been basically destroyed. It turned into dust and fragments. And less than half a year later, we're approaching for our second orbit here, our second periapsis of Sagittarius A, and basically looks like we've achieved a stable orbit around it. So this is going to be our life from now on. Extreme tidal effect, a lot of stars in our skies, and a lot of dangers of living next to a central black hole. And that's essentially... oh, also that happens apparently, we do lose some rocks. Yeah, well that at least will warm up our planet. And anyway, so hopefully now you know what would happen if our solar system approached the central black hole relatively close, and what would basically occur to both our planet and our solar system. And so this right here is Sagittarius A, which is the supermassive black hole at the center of our galaxy. It's absolutely gorgeous in the new 9.80 space engine, and it's basically a lot more realistic now than it has ever been. But you're about to see it in a very different view, and here we go. This is what I wanted to show you. This is actually an idea I got from someone on Reddit to basically decrease the exposure level to the maximum, to the point where basically you have no more exposure. And this would of course turn any black hole or any other bright object very, very, very dark. Now this actually to me looks absolutely terrifying, and we're going to come a little bit closer, so brace yourselves. Now, if this actually is a real black hole somewhere out there in the universe, it might actually look like this, especially if it's in a very dark sort of part of universe where there's really nothing else there. But this is absolutely amazing and also terrifying at the same time. I'm trying to position myself so that we can actually see it a little bit better. But anyway, so yeah, so let's talk a little bit more about some of the knowledge of black holes that we currently have, and some of our understanding of these beautiful, terrifying objects. Or are they objects? I don't really know. I don't think anybody does. They are definitely a phenomena that will one day hopefully help us understand the universe a lot better, because I personally believe that as soon as we can actually understand what's going on with these things, we'll have a grasp on life to the point where we'll probably know a lot more than we currently know about ourselves and the universe, of course. Now, so these objects were originally predicted by Einstein back in 1916. But he, of course, didn't really call them black holes. This term originated something like 50 years later, and it was actually originally coined by someone by the name of John Wheeler in 1967. He was actually a very famous astronomer, and so he was the first to actually describe these as black holes. Now, what we're going to do right now is actually possibly move away from this, and we're going to take a look at one of the first black holes ever discovered. Actually, not one of the first. It was officially the first black hole to be ever discovered, although there was a bit of a controversy between two very famous people. And these two famous people were, of course, Stephen Hawking and Kip Thorne. Kip Thorne is actually the person who was responsible for the super realistic representation of black holes in the movie Interstellar. He's a very famous scientist as well. And basically what they argued about is this black hole that I'm about to show you, called Cygnus X1. They argued whether it was a black hole. So Kip Thorne said that it was, and Stephen Hawking said that it wasn't. And by 1976, I believe, it was actually proven that it was a black hole, and only in 1990 did Stephen Hawking finally admit that, okay, yeah, I was wrong. Anyway, let's actually go take a look at it. You can easily find it in Space Engine by typing Cygnus, and it's actually in this system right here. There's two objects, and you'll find out why in a second. I'm actually going to reset my exposure for a second. Oh boy, this is really bright. Hopefully I didn't blind you with this. But this is what the actual black hole looks like in Space Engine if you have your exposure at a regular level. So let's go to Cygnus X1. We're going to jump to it, and it's actually a binary system. There are two objects here, and the first object, as you can see, is a very, very bright blue luminous supergiant. And if you look really closely, you'll see that there's another object right here. Now, this is not a star. this is actually the black hole that we're talking about. You can kind of see their orbits if you click this button right here. And Cygnus X1 is essentially the first official black hole we have discovered. It is not very far away from Earth. As a matter of fact, if I check the distance here, Earth is approximately 2100 parsec away, or something like 7000 light years away. So even though we can't really see the black hole itself, we definitely see this star and the effects that this black hole has on this star. But anyway, let's actually approach it and let's take a look at it as well. And here it is. Here's the beautiful black hole Cygnus X1A. Now this is actually not in real time, but this is. And as you can see, it still has its accretion disk spinning really fast. This is because this is actually what's known as a stellar-sized black hole. It's only about 16 masses of the sun. And so here, things spin really fast. And we're going to approach it a little bit closer just to take a look at it. I'm also going to slow down time so you can actually see the spinning accretion disk. Now, if you were to approach this black hole that close as I am right now, you would currently basically be stretched into what's known as a space spaghetti, and you would very likely die. With supermassive black holes, it's a little bit different. You can actually approach them relatively close, but here you would already be dead. And so these types of black holes are actually almost everywhere. We think that there might be even up to 1 billion of these in our galaxy right now. We just haven't found them. But there's quite a lot of these stellar mass black holes pretty much everywhere. Now, except for stellar black holes and supermassive black holes, which we just saw, there's also something called intermediate black hole. Now, these are actually still kind of theoretical because we may have only discovered one of them. There's a galaxy called NGC, I'm going to see if it's actually here, NGC 2276, and inside this galaxy, somewhere out there, we found an intermediate black hole. Now, I don't think it's actually present in this game right now. It's called NGC 2276-3C, which is not an object on this list, but somewhere in this galaxy that's about 200 million light years away from us, there is an intermediate black hole that's about 10,000 masses of our sun. Now, we think that these particular black holes are formed when essentially a star cluster collapses into a black hole. Not just one star, not just two stars, but like something like 100,000 stars collapse and create these black holes. But when it comes to the black holes in the center, the supermassive black holes, they are formed in a very mysterious way. There's actually quite a lot of theories about how they form, but I believe one of the more prevalent theories is that they were there from the beginning. They're so-called primordial black holes. They were there from the start of the universe. They were always there. Now, another interesting thing about these supermassive black holes is that when the... let me just actually show it to you first. When the matter enters the black hole, some of it actually gets bounced off the event horizon and creates these particle jets that basically move away from the black hole in two directions. And these particle jets are, well, first of all, they're fascinating, but they're also responsible for some of the brightest objects in our universe. The so-called quasars and blazars are essentially that. They're basically supermassive black holes in some other galaxies that are kind of pointing toward us, like in this fashion essentially, and their particle jets are aimed directly at us, and they're so bright that we can see them from billions of light years away. Now, another really fascinating thing related to black holes is actually in regards to quantum mechanics. Now, there is something called Hawking radiation. Actually, Stephen Hawking came up with it when he was explaining how quantum mechanics may affect black holes. So what he basically suggested is, let me just come closer to the event horizon so I can actually explain it to you in a little bit more detail, and so you can actually visualize it. We're going to turn this back into this terrifying black hole that you saw before. And we're going to also approach the event horizon a little bit closer here. So in quantum mechanics, there are particles and antiparticles, which are basically created at all times. They're essentially matter and antimatter, and it's created everywhere at all times, and then it also may create some energy, but basically this is the main principle of quantum mechanics, that particle and antiparticle can combine and create energy, or sometimes energy may create particle and antiparticle. Well, black holes, of course, have a lot of energy, and so they also create these particles and antiparticles. But sometimes one particle, or I guess just a particle, might be created on the inside, but the antiparticle might be created on the outside. And when this happens, one of them essentially falls into the black hole, but one of them escapes. And because of this escape, and because of the connection of particle and antiparticle, the actual black hole loses a little bit of itself. It loses a little bit of mass, it loses a little bit of its, I guess, energy. And due to this loss, with time, black holes will actually disappear. They will eventually evaporate, and this is what we refer to as Hawking radiation. Now, it's a very interesting and fascinating idea, and we're going to talk a little bit more about it when I talk a little bit more about black holes, because I actually want to cover this topic a little bit more. But I guess for now, what you need to kind of understand is that sometime in the future, in like really far future, all of these dangerous, scary-looking black holes in our universe will essentially disappear. Now, whether it's going to happen before the end of the universe or whether it's going to happen sometime before the end of the universe is another question. But theoretically, even the supermassive black hole in the center of our galaxy is one day basically going to completely disappear, and there is going to be nothing left. So in the previous video, I showed you the third or fourth most massive ultra-massive black hole, and today we're going to talk about another one. We're going to actually recreate it from scratch using Universal Box, but we're going to have trouble, and I'll show you why. First of all, let's actually go into the simulation called Supernova in Galaxy, and we're going to basically get rid of the extras here that we don't need. We're going to zoom in on the black hole here, and place a star in orbit around it, and we're going to choose the largest possible star in terms of size. And so I'm going to place UI Scuti in a very close orbit to this black hole, and then we're going to zoom into the star and actually erase the black hole. Now, where I'm going with this, you'll see in a second. I'm actually trying to create another black hole here that is going to also be a quasar, or I guess in this case it's going to be a fake pulsar. Now if I enable realistic mode, it will actually go supernova, and if I do it again, it's going to become a blue giant. And here, if you go to the bottom, there's a button that's going to appear in a second that's going to be called Make Pulsar, and here it is. So now we've made a pulsar, and we're going to basically increase its power by increasing this number right here. And we're going to look on the outside just to see if this is actually looking like a pulsar. And here we go. So we've made a galaxy that kind of looks like basically a quasar. It's essentially a very bright galaxy that is pointing its relativistic jet, which is this thing right here, directly at us. And it looks like this. Now, I'm going to rename this into S50014+81, which is essentially the name of this particular galaxy. And this is essentially what it might look like from a distance, basically from being somewhere close to it. It's a very large quasar with an ultra supermassive black hole. Now this black hole is actually a lot more massive than you see in here. It is, as a matter of fact, 40 billion suns. But the problem in this particular simulation is that it will not change the size if I actually change this. The size of this black hole remains as 7.94 astronomical units, which is the size of US Scuti. Now, this is, of course, a bug. This is a bug in the game that allows me to create this or relativistic jet, and also allows me to turn this particular star into essentially a black hole of the same size and mass. But unfortunately, this is not a very good representation of this particular galaxy, because this actual black hole is a lot larger. So 40 billion masses of the sun is essentially something like 10,000 more than the black hole that we have in the center of our own galaxy. So our black hole, known as Sagittarius A star, is a lot less big. It's basically a lot smaller. It's a lot less massive, and you can kind of see how the other supermassive black hole dwarfs our tiny Sagittarius A. But this is actually not even the full size. Like I mentioned, the size is actually much bigger. As a matter of fact, the actual size of this black hole is approximately this big. It's about 1600 astronomical units in radius. And so to demonstrate this, I'm going to go into another simulation, because unfortunately the game does not allow me to increase mass or increase size of this black hole. I can increase the mass, I just can't increase the size anymore. But before we do this, let's actually just briefly talk about this actual quasar. Now, it is ridiculously bright. If I were to place this quasar at a distance of about 200 or about 300 light years away from our sun, it would be just as bright as the sun. It would actually provide us with just enough energy to be a sun. And this is at a distance of about 280 light years. Now, also in comparison to our own Milky Way, or I guess all the stars in our Milky Way, this quasar is about 25,000 brighter. It is ridiculously bright. And every single year, this beautiful black hole absorbs something like 4,000 masses of the sun. So it actually swallows 4,000 suns, and let's just demonstrate this. So it swallows 4,000 suns every single year. And I think I accidentally destroyed my black hole by smashing suns into it and by causing supernova. But anyway, let's actually go into the different simulation now and talk a little bit more about the size of this thing. And so using the regular solar simulation, we're actually going to compare the size of our own solar system to the size of that ultra supermassive black hole. So let me just zoom in for a second. There's Earth, there's Mars, there is Vesta and Ceres, there's Jupiter, we have Saturn, Uranus and Neptune. And now as I zoom out to the distance of about 1600 astronomical units, I'm going to demonstrate to you the actual size of that thing in terms of just using this golf ball, basically, in terms of the solar system. So this is approximately 1600 astronomical units, and this is actually the size of that humongous black hole. Now, this might not actually give you a good idea of how big it is until I create this right next to our solar system. So let's do that. Let's actually take, let's take a pool ball number 8. And we're going to just kind of make it orbit around our solar system at a distance of about 2,000 astronomical units. And then we're going to zoom into it and make its actual radius same as the radius of this particular black hole, known as S50014 plus 81 central black hole. And so once I change its size to 1600 astronomical units, it's going to become this big. I don't know if you can see it, but it's right next to our solar system, and it is absolutely ginormous. There it is. This whole darkness in front of you, this is how big that black hole is. Now I'm going to go to Earth for a second, and so there it is. You can kind of see the edge from our planet Earth, and it goes all around our solar system, and basically that is the size of that ginormous object. I can also go into charts here. And as I zoom out from our sun, you'll see that the sun actually makes a reflection here, but the actual black hole is, it's kind of hard to see, but it's basically right here. It's this huge object. And so what I'm going to do now is I'm actually going to release the timer, and let's see what happens if I basically let everything fall into this huge 8-ball black hole. And why is it called 8-ball black hole? Because I actually used the 8-ball or pool ball 8 to make this, to make this black hole. And it's not really a black hole, it's just an 8-ball, but looks like this 8-ball just destroyed everything in like literally less than a second. Okay, let's actually just try this again. Maybe I'll put it a little bit further. And so now I decided to put it at a distance of a few light years, and here we go. I'm going to release the timer again. Let's see what happens to our solar system. I think it's going to be attracted to that black hole and move at a ridiculously high speed. Whoa, that's impossible. It's moving at faster than the speed of light. Now, what's going to happen next is anyone's guess, but this actually looks kind of cool. So we're basically approaching this pool ball 8, and we're going to, I'm guessing, smack into it any second now. Now, I wonder if this is actually going to crash my game, because I might actually reach some kind of a interesting phenomenon that we've never observed before. And here you go. You can actually see everything being spaghettified because the gravity here is a lot stronger than the gravity here. So the entire solar system is being spaghettified, and boom! Look at that. Everything destroyed. That was surprisingly cool. That was actually a really cool destruction of our solar system. Thank you, Pool Ball 8. You have been a very interesting black hole to simulate. And anyway, so that's essentially what this supermassive black hole might look like and how big it is. And in the previous part, I also show you the other quasar that also has one of the brightest and one of the most massive black holes that you can find in Space Engine. And so I hope you learned something from this video, and I hope you enjoyed this little explosion that I just created. And let's actually just do it again right before I finish this video. And anyway, thank you so much for watching, everyone. I appreciate all of your support. Game you later, and as always, bye-bye. What did I just do? What was that? That is awesome. I think I've just discovered some kind of a really cool effect. And what did I just create? And turns out this is some kind of a interesting red looking black hole. That is awesome. That is really, really cool. I'll see you guys later. Bye-bye. Once in a while, I discover a video game that is unknown to most people in the world, but is absolutely incredible at teaching you something really, really awesome. And this is the game you see in front of you. It's a game called A Slower Speed of Light, and it's a game made by the MIT University, specifically part of a university called the Game Lab. I believe it's actually several people that you can kind of check out in the credits here. And they, what they did is they actually used the Unity engine, and they used a mod called Open Relativity to basically create this absolutely incredible simulation of what happens when you move closer to the speed of light. This is a continuation of the previous video I made about black holes and approaching the event horizon. Today I'm going to demonstrate to you what happens to the world as you move closer to the speed of light and how the world changes in front of you and also behind you. Welcome to What the Math. So we're going to actually start the new game right here, and it's going to load really fast. So basically all this game does is demonstrate to you how the speed of light or velocity closer to the speed of light changes the world around you. Once upon a time, in a quiet village, there was a little child. Sadly, the little child fell into the death's icy grip far too soon. The little child's spirit began the journey to become one with light. But the speed of light was too fast for the small and clumsy little spirit. Luckily, the spirit world is full of magical orbs that slow down light. Collect orbs to slow down light to walking speed so you can finally move on. This is how many orbs you collect, and this actually represents the percentage of the speed of light, and this shows you a comparison between your speed and the speed of light. Although this is actually kind of tricky to figure out, this is more easy. Basically, it gives you a percentage, and this will, here will show you the light that you're observing. So at some point you'll be able to see ultraviolets and also infrareds. And the controls are here. So let's start the game and look at this brilliant little game as it loads. So essentially, you're moving regularly, and here what you're doing is collecting orbs. Now, unfortunately, the controls are relatively challenging because you're kind of moving like a tank, but that's because the idea here is that you represent a kind of a spaceship. So if I wanted to move sideways and look into my side window, I could do that this way. I can just move using D and S, and I'll be able to see what a spaceship would see from a side window. And that's, of course, to make this a little bit easier to visualize. Now, every orb represents 1% of the speed of light. I'm going to get to about 25%, and as I'm getting these orbs, you'll see that the color in front of me changes. And the reason why this is happening is because as you move closer to the speed of light, the light in front of you, the light that's coming toward you, is being blue shifted. It's being moved and stretched towards the higher energy spectrum of light, and you get to observe light that's a little bit more highly energetic. So here, let me just stop for a second. This is what the normal world looks like. Now, I'm going to move at 25% speed of light, and this is what you see. It gets a little bit more bluish, a little bit more greenish, whereas behind me the opposite happens. I get to see the light a little bit redder. It's more red, it's more sort of dark because it gets red shifted. So I'm going to get to about 50% of the speed of light and demonstrate to you what happens then. But even at this slow velocity, the world looks quite different. It's a lot more saturated, it's a lot more visually, I guess, scary. At least to me, it looks a little bit scarier. And the other effect that you'll start noticing is the so-called stretching effect of the world that you'll see more pronounced when we get to higher speeds, higher velocities here. So let me get to 50 and I'll show you what happens then. actually not even 50. Look at what happens when I'm at 43 percent of speed of light. The world is completely different. It's a lot more ultraviolet. It's a lot more saturated with higher energy sort of colors, I guess. And here we get to see a lot of ultraviolet. We get to see a lot of colors that we don't really see otherwise. So our eyes would not be able to see any of these colors. This would be very, very sort of high energy particles, and the world would actually look very dark to us. And behind us, the world is very sort of dark and red and kind of gloomy. So I'm going to get so right now we're at 50. We're going to get to 75, because that's when we'll get to observe the effects of stretching as well. It's not as pronounced yet, but it will become more pronounced as we get closer and closer to the speed of light. And look at that. Did you see this for a second? So there's nothing here, right? And if I start moving toward it, you'll see that there's actually something on the bottom. And that's because we actually see ultraviolet radiation now. So whatever this is, it emits ultraviolet radiation that was invisible to us before. And so as you're basically moving towards something at a velocity of 60% of speed of light, even though previous colors are invisible to you now, what was invisible before has now become visible. So a lot of the light that used to be infrared, sorry, did I just call this ultraviolet? It's not actually ultraviolet. Originally what this is infrared. So whatever this is just infrared to us and would not be visible because we don't see infrared. But as you're moving toward it, it changes into a color. So the infrareds, original infrareds, would become normal colors now, and whatever was normal color will become ultraviolet, and vice versa. So if whatever's behind us and is ultraviolet will become regular color. Oh my god, this is so scary. This is scary and red. Look at that. And whatever is so whatever is behind us and is high energy will actually become regular color. And if I move inside, or basically if I look into my side window, this is what I would see. In front of me, it's slightly more blue. Behind me, it's slightly more red. But right in the middle, it's actually normal colors. So the side windows of my spaceships, or I guess my vessel, my spaceship, would actually see regular colors as they're moving against us or moving next to us. We're going to get to 75 and see what happens then. So let me collect these orbs. It's a little bit more trickier than you think because I am moving like a tank here. And at 73, this is what you get to see. It's a lot more saturated. It's a lot more unappealing. But this is essentially what the reality would look like. You would have these really, really highly saturated objects. The side view would be this, and behind us would be complete darkness now, because a lot of the colors, even the colors that were ultraviolet, have now actually been stretched into the invisible light spectrum. We cannot see those lights anymore. We cannot see those colors anymore. They're now sort of invisible to us. And one more thing you may notice is this. As soon as I start moving, look at how the mushroom in front of me actually will look more far away. That's because we now also are experiencing the stretching effect. And this is, of course, because as you move closer to the speed of light, everything in front of you gets kind of stretched. Everything behind you looks a lot closer than before. And this will become more visible as I get closer and closer to the number 90% of the speed of light. Now, what I really like about this game is that it's so simple, but it's so effective at delivering this idea of moving at the velocity closer to the speed of light, which usually is so difficult to imagine. It's actually almost impossible to imagine unless you're Einstein. I think he was pretty good at imagining things, but for a normal human being that is not Einstein, it's kind of challenging. But this allows you to visualize both the change in color and the change in stretching. So at 80%, this is what happens. We're going to get closer to 90 by collecting these orbs. Come on, don't get stuck. Here we go. And 83, 84, 85, 86, 87, 88, 89, and let's stop at 90. So, okay, at 90%, if I'm standing still, the world is normal. If I'm moving away from something at 90% of speed of light, this is what I would see. It would come close to me, become really dark, and I would see almost nothing. If I'm moving towards something, this is what I would see. It would get really highly saturated. It would be really, really bright. And I'm really sorry for making... Your eyes will probably hurt just as much as mine do right now. I'm sorry for making this sort of, I guess, hazardous to people with epilepsy, because I think this is how epilepsy gets triggered as well. So you shouldn't be watching this if you're epileptic. But anyway, so this is what you would see this is how the world will look like to you if you're moving at 90% of the speed of light. And this is what your side window would show. Darkness, blueness, or purpleness, and normal world right in the middle. So it's kind of like a rainbow of visibility. It's pretty awesome. All right, so let's get to 99%. We're going to collect 9 more orbs, and we're going to stop at 99%. 1, 2, 3, and here's the 9th orb, and let's collect it, and boom, 99% of the speed of light. Now, this is theoretically possible. Theoretically, it's possible to move at this velocity, but it's just very difficult to achieve. So this is what you would see. The normal world that you see in front of you would look like this. It would stretch into the distance. It would be very highly saturated. It would be a lot of different, very strange colors, and you would very likely have a headache. Behind you, it would be this. Almost complete darkness. You would only see colors on certain objects that emit high frequency radiation. Everything else would be completely dark. And your side window would show you this. So this is what the side window would show in your spaceship. And notice how things do get stretched or zoomed in. If you're looking in the back window, things would look closer to you. If you're looking in the front window, things would look farther away. Let's collect the last orb and you'll see what happens. So at 100% velocity of speed of light, what you would no longer see is colors. So everything behind you would be completely stretched into infinity, into complete and total 9 minutes and 6 seconds. It took me quite a while. So the reason why you don't see colors anymore here is because, or I guess you see regular colors, is because if you were to move away from something at the speed of light, you would essentially see nothing. Everything would be redshifted into infinity, and if you were to move towards something, it would be blue shifted into a very highly energized radiation that would most likely just burn and fry you. So the reason why you don't see colors anymore is because of that. It's just impossible to imagine, but you do see a crazy stretching effect. So if you were to move at the speed of light, or if you were light and you were to look behind you, you would see this. Things would just kind of come closer and closer to you until they would be right in front of your face. And we're talking about the entire universe. However, in front of you, things would look farther and farther away, and you would never really be able to reach them. They would look like this. Oh, I did it again. No. Oh no, that bug again. I accidentally, if you're doing this, if you're playing this game, be careful with the fences. It happened to me before when I accidentally moved too fast through the fence, and now there's no way out. So okay, I'm gonna just start this over so you get to see how this game ends. But essentially, this is what happens to you at the speed of light. Things break, game breaks, the world doesn't work anymore. Alright, I beat my old time, 3:46. I had to start this game over. But anyway, so this is what happens when you finish the game. Let's actually move at the speed of light inside this wide gate. We're gonna come from a distance, hopefully without smacking into anything. And this is a lot harder than you think. Here we go, and score. And the game ends. And you actually get to read a bit of an explanation of what you've just experienced. So it tells you, the end, but what really happened. And what happened is that you've experienced the relativistic Doppler effect, and this is essentially what this game simulates, and so well. You can read more about this as you basically play this game yourself, and I totally recommend playing this yourself, trying it by yourself. And if you do beat my score that you just saw on the screen, post it in the comments below so we actually get to see who gets to do this faster. And this is actually where it explains to you the so-called searchlight effect. Moving to the left, the objects on the left are brighter than the objects on the right. So this is actually the effect of moving sideways and looking into the side window of the spaceship. And the better term for this is relativistic aberration. So now you've learned a new term. And the so-called stretching effect is also known as Lorentz transformation, and this is what you experience when you move towards something and it gets stretched into almost infinity. The closer you are to the speed of light, the more likely it's going to be infinity, and behind you, you'll experience the opposite. And as you finish this game, I really recommend that you read through these explanations because they basically simplify everything. And so these are the people responsible for making this game, and I totally thank them for making this amazing simulation that is absolutely free and is definitely free for you to check out as well in the link in the description below. Anywho, thank you so much for watching, guys. And of course, thank you Albert Einstein for coming up with this amazing thought experiment that is now actually a video game that is absolutely free to download, something like 107 years after he actually came up with his theory. And once again, this is a game called A Slower Speed of Light, made by the people from MIT University. And thank you so much for watching. I hope you enjoyed this video, and if you did, share it with your friends who might want to learn more about relativity as well. What you're looking at right now is a pulsar. This is the most precise clock in the universe, more precise than any other clock that we have on our planet. It's so precise, in fact, that we've actually been thinking of using these as kind of beacons in space if one day we decide to explore the universe and create an faster than speed of light travel, or are able to visit other stars. But before we do all this, we actually want to find something else. We want to find a pulsar orbiting a black hole. This is actually known as the holy grail of astronomy, because if we're able to find one where a black hole and a pulsar coexist together and orbit around each other, we can use this to study both of them. And specifically, we can actually discover new awesome things about gravity, about special and general relativity that Einstein proposed over 100 years ago. And we can also study very strong gravitational fields and gravitational waves that would be created by the black hole. The theories that we have today, specifically general relativity, make very clear predictions about the nature of black holes, and to prove those theories we would actually love to find one of these things orbiting one, because then we'll be able to prove them. And of course, this would actually show us if Einstein was completely and 100% correct about his predictions, or if he may have made mistakes. And so today, let's actually try to build a system with a black hole and pulsars orbiting around it, and talk a little bit more about why this is kind of cool. Welcome to What the Math. And the kind of a black hole that they want to find is something like this. A black hole that's not too massive, about 5 to maybe 10 masses of sun, and a pulsar orbiting around it. So if we can actually find something that looks like this, and you can kind of see them dancing around each other, we'll be able to use this data to study all kinds of gravitational disturbances created by the black hole, and all kinds of really interesting theories will be finally resolved if we can actually discover this. These systems are actually expected to be very, very rare, but a lot of the astronomers are hopeful that one day we'll be able to discover something like this, because we currently were able to find a pulsar orbiting around our central black hole, the large black hole known as Sagittarius A, which you can kind of see in the game right here. Here it is. It's about 4.3 million masses of our sun, and it actually is very, very large. This is how big it is. This is how large it would actually envelop all of these objects easily. If I were to place this right here, it would actually possibly just suck them all in an instance. There we go. Let's see what happens. So there they go, flying toward it as they're still orbiting around each other. And basically, these two objects are gone. So there is a pulsar orbiting around Sagittarius, but to study the gravitational waves and to actually study all of the things we want to study, we need to find one that's relatively close to Sagittarius A. Unfortunately, we haven't found one yet. The one we found is really, really far. It takes many years to orbit around it, so it's not as good for us. And so what we're going to do is we're going to try to create a system where Sagittarius is right here, and we're going to have a bunch of pulsars orbiting around it. Now, to do that, or the easiest way to do that, I actually discovered that if you use a star called WD, WD1142645, oh, where'd you go? 1142645, also known as carbon white dwarf star, you can basically place these anywhere you want, really. I'm going to just place one here, one here, one here, one here, and a bunch more. And we're going to have some orbiting in other ways, other fashions as well. And so here we go. We're going to place them everywhere. And you'll see what I'm doing with this in a second. So let's just say there is a black hole, and I'm sure somewhere in the universe there is one that sort of is like this, where you have a bunch of, specifically here is going to be neutron stars orbiting around it. So, alright, I think that's enough. Now we're gonna stop this for a second and go into properties for each of these little guys. Scroll down up to the point where it says make pulsar, and then we're gonna click this button. Now, you'll notice that initially it makes it so that its streams are too small. So we're going to actually go right here and increase this by 10 times. So it's going to be at least 3 and how many zeros is this? 9 zeros, I think. You can make it bigger if you want. You can actually make this even 100 times bigger, but then it's way too big. I don't think it looks as good as if it was just 9 zeros. All right, so here we go. And do this for each one of them, and then what you get is this. And if I start the simulation now, you'll see that all of them are orbiting this beautiful black hole in a very interesting fashion. So this is essentially the little dance of, let's actually remove this, little dance of the pulsars around the black hole. Now you can change the rotations and, so not the rotation, but the actual spin of each one of these pulsars by going in here and changing the magnetic pole degrees. So here I can actually make this 45 degrees and it will actually have a slightly different spin. Now these spin really fast, so you actually have to slow down to see what's happening. Go into seconds per second and you'll see that some of them have a very interesting spin. And if you want them to spin even more, what you can do is you can also go into motion and then tidally lock each one of them, so they actually start moving a little bit when they're orbiting the black hole. And if you want to give them a little bit of a wobble, under motion here and angular velocity, if you give this value a little bit of a setting, like for example 0.1, here you go, here's one that starts wobbling a little bit, and you can then go into the magnetic pole angle here and change it a little bit. If you don't like it wobbling too much, make it lower. If you want it to wobble even more, make it higher. So here's a 40-degree wobble that sort of looks like this. Now I'm going to try to play around with this just to make it look a little bit better, and let's see what we can get here by basically changing all of these and making them really different from each other. And so here we go, all of them are basically flipping around and spinning in very different fashion, and you can accelerate this just to make this a little bit more crazy. But what's interesting here is that, so because this is a black hole and because it's obviously very massive and it creates a very large gravitational field around it, and so here we go, we have a bunch of pulsars going around the black hole in a very interesting fashion. All of them are basically spinning and flipping in different ways. So it kind of looks very unusual and very cool. And it's very possible that somewhere out there is a galaxy that has something like this, a bunch of pulsars orbiting around a very massive black hole in the middle. And so what we might see from a distance is something that looks like this. We see light dancing around and changing its luminosity and changing all kinds of radiation that it sends out toward us. So sometimes it's going to be X-rays, sometimes it's going to be gamma rays, sometimes it's going to be just pure light. And if we zoom out, it sort of looks like this. It's a very interesting luminous object that will definitely change its brightness quite a lot. And so what it made me think about is one of the previous videos from last week was about quasars and blazars, and what we know about them is that they are very luminous and they do change their brightness. So for all we know, maybe one of those blazars or quasars that we're looking at right now is this, because here we have what we know about, for example, blazars, is that they always change their luminosity. It's never predictable, and in a sense, it's actually similar to what you see here. So they do send out a lot of various types of waves. So it's not just X-rays or gamma rays, it's actually everything rays. And our previous explanation about it was that it was most likely because of the way that matter is accreted and sent out into the outer universe using the black hole. And I think I kind of explained in the video, we're not really sure how exactly it works. We just know that it sends out two sort of rays from the central black hole. So one goes up like this and one goes down like this, and one of those rays is pointing toward our planet. Now that's one explanation, but you know what, I kind of like this explanation as well. What if it's actually a black hole that has a bunch of awesome pulsars around it? But anyway, just finding at least one black hole with a pulsar next to it would be pretty awesome. So like I said, they're actually very rare. We still haven't found one where they're relatively close together. And once we find one, you'll actually probably know about it because it's going to be all over the news. It's something that's astrophysicists and astronomers have been looking for a really long time. Anyway, let's actually do something different. Let's increase magnetic field value here by 10, and let's see what this looks like when we actually do that. Alright, this is going to be really bright, but here we go. Look at that, this is awesome. So this is what a very bright black hole with a bunch of pulsars might look like from a distance. And look at that, this is pretty far away and we can still see it blinking and shimmering in the light. And so, like I mentioned before, because of the number of galaxies out there, it's very likely that there's at least one that has a very massive black hole and many pulsars orbiting around it. Whether it looks like this or not, that's another question, but it might exist. And whether one of the pulsars or quasars that we're observing currently are actually this is another question. Now, what do you guys think? Do you think that possibly one of the quasars, or possibly even all of them, are actually this and not what we thought they were? What if it's actually a black hole covered in pulsars? What if it's actually, this is why we see so many different really luminous, really bright objects in the sky, and we just don't really know what they are? And of course, this would explain why we actually do see things like X-rays and gamma rays coming out of quasars, but it would not explain why we see things like radio galaxies, because radio galaxies, quasars, and blazars are obviously related. It's the same object, just from a different angle, like I explained in the previous video. But I think it makes for a pretty interesting hypothesis. So if one day we'll find something similar to this, it will explain quite a lot about the universe and will of course finally help us understand gravity and gravitational field a lot better. And so what we're going to do first is we're going to take a look at the largest supermassive black hole available to us in Space Engine, which is unfortunately not the biggest out there, but nevertheless it's better than nothing. So we're going to go into the search box here and type APM. Now this is this is a galaxy called APM 082795255, but right in the middle of it is the central black hole that's also available in Space Engine. And so here we go, this is the galaxy APM 082795255, a galaxy that's about 12 billion light years away from us and is actually not very big. It's not a very large galaxy, but right in the middle there's a supermassive black hole that's a huge percentage of the total mass, and it creates a very interesting environment. Inside of this region right here, there is quite a lot of matter that actually falls into this black hole and creates a huge amount of energy. Now, unlike other quasars, this one, and this is actually a quasar because basically it projects a very bright sort of ray toward our planet Earth that we can see from really far away. But yeah, unlike other quasars, this one specifically doesn't have the relativistic jets that usually make it even brighter. But it does have a very large active nuclei region that produces a huge amount of energy. And as a matter of fact, this used to be one of the brightest objects in the universe until one of the other ones was found. But here specifically, what's interesting about it is that we've also detected quite a lot of water from this region. As a matter of fact, there's so much water here that we think that this is probably the largest amount of water present in one spot in the universe. And so here we have something like 100 trillion times more water than on Earth. All of it is sort of in this central region. But the important finding here, of course, is that we now know that there was water basically from the beginning of the universe. So what we see from this galaxy is light that's about 12 billion years old. So even 12 billion years old, 12 billion years ago, there was water in the universe, meaning that maybe some of the water on Earth is actually a lot older than we can even imagine. But anyway, let's actually go to that actual black hole. We're going to zoom into it and take a look at it as well. So in Space Engine, this black hole has quite a lot of various stars orbiting around it. You can display them by pressing this button right here. And it's a very massive object. It's a huge object. It's a lot bigger than the Sagittarius A star in the center of our own galaxy. And here, basically, the mass is something like 23 billion masses of the Sun, which is in comparison to 4.3 million in Sagittarius A, which is our own supermassive black hole, is a tremendously large amount. So this is a super ultra massive black hole that creates a lot of energy and also absorbs a lot of mass so that this energy can be created. Now we're going to accelerate time here a little bit just so you can see what it looks like when the accretion disk spins, and you'll get to actually enter this particular supermassive black hole as well. And so here we go, and boom, we're gone forever. Now let's actually look at some of these stars that are orbiting around this supermassive black hole as well. I'm going to accelerate time just to show you that some of them only take, I think it's actually less than a year orbit. As a matter of fact, here, the one orbit is about 314 days, and that's very, very little compared to one of the stars that orbits around our own black hole, which usually takes about 16 years, and that's the closest star. But if we move a little bit farther away, you'll see that there's actually a lot more stars on the outskirts as well, and you can kind of accelerate time just to see what it all looks like in fast forward of about 10 or 20 years per second. So this is what the supermassive black hole does to all of these stars, and many of them lose matter that falls into this supermassive black hole to create all of the light that we can see from our planet Earth. Alright, so now let's escape this galaxy and leave this black hole, because I actually wanted to show you something really cool about this particular galaxy. Now, Space Engineer creates quasars relatively well, at least to some extent, when it comes to brightness. If you actually leave this galaxy and you move far enough away from it, the quasar effect kicks in, and you'll actually get to see the real brightness of this particular galaxy from a distance, or essentially what it would look like to us from Earth. So after 12 billion years, this light has reached us and kind of looked like this. And this is absolutely incredible. So this is the galaxy we just came from, but it is now displayed as a very, very bright quasar, which is essentially what it really is. It's a very, very luminous object, and even if you move away, far, far away from it, you'll still be able to see it. You don't even see these other galaxies, but you still see the quasar, known as APM 082795255. And I'll actually have to move away quite far away for me not to see it anymore. I can see it even from 1 billion light years away. And you can't even see our galaxies that far away. And let's wait until it actually finally disappears, because I actually want to see what distance I have to be at for me not to see it anymore. And 3 billion light years away from it, we can still kind of see a little spot in the middle. There's actually another one right there. That's another quasar. And I think right about here, maybe 4.3 billion light years away, that's when you can barely make it out. It's barely visible. But that's essentially how quasars are, how bright they are, and how we can actually see them from our planet Earth. Now, in the beginning I mentioned that this was 12 billion light years away. That's, of course, it's a mistake. The light has traveled for 12 billion light years, but in reality, because this quasar has always been moving away from our planet and from our star system, it's actually much farther away by now. In reality, this object is now something like 23 billion light years away, and we'll never ever be able to see what it really looks like now. And anyway, in this part I just wanted to show you this particular galaxy, but in the next part, which will be out tomorrow, I'm going to try to recreate another really beautiful object, another quasar, that is actually the most massive black hole in the universe that we found to date, using Universe Sandbox 2. And to find Sagittarius A, we're only going to be using Space Engine today, because I figured it's about time that I just spend time with this really awesome simulator that a lot of you have been asking about. Space Engine, as you may actually know, is absolutely free, and unfortunately it's only available for Windows, but if you do have Windows, or you can emulate Windows on your Mac, you should definitely get this, because look at the beauty that it creates. This is by far the best space simulator out there. Hands down. I'm sorry, Universe Sandbox 2, you're great, but you know, nothing beats free, and this is definitely amazing. Anyway, so how are we going to actually look for this amazingly huge, massive black hole, especially considering the fact that you can't really see black holes? They're, you know, they're black. That's why they're called black holes. You cannot really see them. You can only see the after effects. And so as I'm actually moving closer to the center of our galaxy, faster and faster, so and you can kind of see the stars swimming by us as I'm approaching the center of our galaxy. I'm just gonna tell you a little bit more about how this particular black hole was detected, and it's actually not very tricky. As a matter of fact, the reason we actually are almost 100% sure there is a black hole right at the point where I'm going is because of another star, a very large star, about 15 masses of our sun, that is actually relatively bright as well, that orbits around this imaginary or invisible point and you can kind of actually see it orbit. We've actually seen it orbit around that point, and its orbit only takes it about 15 years. So there's this star somewhere in the middle, and it's just called S2. And S2, you can actually see the picture here that shows you the orbits, all of these stars. So the orbit of S2 only takes it about 15 years, and it's really interesting because it actually moves really, really fast at about 5,000 kilometers per second. And at this speeds, it's impossible for it to be anything else but a very, very massive black hole that creates this kind of effect. Now, all right, so that's good. We know that there's a black hole somewhere here, but unfortunately, because as you can see, it's really, really bright here, it's actually almost impossible for us to detect it. So we can only see it using the effects of other stars, or basically seeing the orbits of other stars and then trying to estimate where exactly it's located. But anyway, we'll never really find it if we just fly around our galaxy. We just have to do this a little bit differently. We're going to actually click on this button right here, and this allows us to search for various objects within a certain distance. So let's actually look for everything that is a black hole within the radius of about 10 light years from us. So we're going to actually just click on OK here, and then click on search, and well, it looks like there's nothing around us. However, if I change this to 100 light years, if we actually increase the search radius, we will be able to find, look at that, at least 3 different black holes. Now, how do we know if this is the actual black hole we're looking for? And the way you can tell is usually by the number of stars orbiting around it. So this one seems to be pretty massive, so let's see if this is what we're looking for, although I'm pretty sure it's not, but we're actually just going to go there and check it out. So I think this is one of the black holes nearby, but it's probably not the one we're looking for. And by clicking on this button right here, I can actually see that this is not the black hole I'm looking for. As a matter of fact, this is a binary system where there's a brown dwarf and a black hole having a Berry center. And this particular black hole is only about 10 times the mass of Sun. So it's actually very, very small in comparison to the Sagittarius A, which is 4.3 million times of our Sun, which is actually much, much, much more massive. So, all right, let's try this again then. And having searched again using 1000 light radius, I found a few more black holes, but once again, none of these are actually massive enough for us to actually consider them to be Sagittarius A. But you can see there's actually quite a lot of black holes within 1000 light years of this particular location, so they're not very uncommon. They're actually pretty common. All right, so well, that's good. Let's actually try to go a little bit more into the middle of the of our galaxy and search again, but this time we're going to increase the radius to about 10,000 light years. So I'm actually, to do this even more effectively, what I'm going to do is I'm going to fly out of the galaxy just to see where approximately where the center is, and it's actually somewhere in here. So, and then we're going to just very gently approach the center, and right in this location, as you can see, there's a lot of stars. This is a very highly concentrated area, and we're going to search for it again using the same principle. And we found a lot more black holes near the center, but if you look at if you sort them by stars, if you look at this one, this has 23 stars. Alright, so that looks really interesting. So let's actually go to this particular black hole. We're going to go to it and see if this is actually what we're looking for. And oh my god, look at the size of that thing. This is already very, very large. Look at the gravitational lensing effect that it even creates. And so this is a pretty massive black hole. If I actually click on it, you'll notice that it says that the mass here is not even listed. As a matter of fact, if I actually click on this object, it says Galaxy Milky Way. And if I were to right click and info it, it says this is the Milky Way. So essentially, this is the center of our galaxy, and we were able to easily find it just by going into an approximate location of a center and then looking at all of the black holes within 1000 light years of that location. Now there's another one here, and it's a pretty massive black hole as well, and there is actually another black hole orbiting around this the central black hole, and that other black hole is actually quite massive as well. It's about 1,300 times the mass of our Sun, and it was discovered in 2004 by a group of scientists. And what's really interesting about the other black hole that orbits around this central large black hole is that it actually shows us, or it gives us an idea of how these massive black holes at the center of the galaxies are formed. So what scientists think today is that the other black holes that orbit around it eventually get sucked into it and increase its mass. And this sort of gives you an idea of how all of these galaxies are created. So in the beginning, this might have been a very small black hole, but as it absorbed more and more massive black holes from vicinity, it basically became an ultra-massive black hole that it is today. And what's really interesting about the Sagittarius A is that we know that it has an accretion disk. So there's an accretion disk that has a distance, or it basically orbits around the black hole at a distance of very close to the orbit of Neptune in our solar system. So it's a very, very large, very wide arc. And this accretion disk actually emits radio waves that we can receive from Earth. And we actually know that there is something going on here, and it's very likely an accretion disk from a black hole because of this radio wave emission that we can actually hear on Earth. And what's even cooler is that once in a while we'll even detect some crazy X-ray emissions, really powerful X-ray emissions from this region. And the only explanation we have for those X-ray emissions, especially the one we actually were able to detect in January of 2015, is that something like an asteroid or a small planetoid probably smacked right in the middle, or basically approached this location and fell into the black hole, and then as a result of the collision with the black hole, it emitted a very, very large amount of energy. And there's quite a lot of these X-ray emissions that have been detected because we are actually always looking in this direction. There's actually a telescope that is always monitoring this black hole, just looking for more stuff to discover and more unusual things to see. And actually, one of the cooler things that they saw relatively recently, starting in 2008, was what you see on the screen right now. They actually were able to see a cloud of gas passing by very close to this location and getting sort of disrupted by it. And there's an artist rendition of what possibly happened. I think people or scientists basically think that it may have been a star that approached the black hole really, really closely, and it just got broken up into little pieces because of what's called a Roche limit, and also because of the fact that there's a very strong gravitation here. And so as this object approached the black hole, it got broken up into pieces and basically created the cloud that we got to detect. Now, what I wanted to see is actually this. I wanted to accelerate time and just watch these stars that are close to it orbit around it. And you'll actually see that they orbit really, really fast. So we're going to accelerate time so that it's possibly something like 1 month per second. There we go. And you can see how fast they orbit. So there's our stars, and these actually don't have the same names as they do in real life. But these are the stars that we can actually see orbiting around this imaginary location in real life as well. So there we go. This is a little bit better. This is maybe 4 months per second. And there we go. And there's actually a lensing effect that you can detect in Space Engine, but unfortunately we cannot see the lensing effect from Earth because, like I mentioned before, there's so many other things in between this black hole and our planet Earth that we just can't really see it very well. It's a little bit difficult to see. But our planet is not actually that far away from it. It's only about 26,000 light years away. And one orbit of our star, our sun, takes several 100 million years. Or actually, I believe it's 150 million years, around there. Whereas these stars, they orbit really fast. So the fastest one is 15 years. I think the slowest one is maybe about 35 years. But they all are basically orbiting around this very, very massive black hole, and they're doing it really fast. Now, because it's not really even close to the speed of light, they're obviously not going to experience anything close to what we saw in the movie Interstellar. So Interstellar was a little bit far-fetched. This has to be a supermassive black hole that also spins really fast to create time dilation effects that we get to see in Interstellar. But here the time dilation effects would be very, very minor. So even on the fastest star, you would only maybe gain a few seconds for every few years. In other words, if you were to live on a planet that orbits one of these stars, which, like, let's just say this star right here. And so if you were to live on one of the planets that orbits this star, you would possibly gain maybe a few seconds for every few years. And so if you lived here and your twin lived on Earth, you would actually be a few seconds younger every few years than your twin. And that's what we call time dilation. And so as we're orbiting around this black hole, which is somewhere here, there it is. It's right there in the middle. I'm gonna try to zoom into it so you can get to see it a little bit better. There we go. So as we're orbiting around it, you can kind of see that not only is there a really interesting motion of other stars that is going on around it, but you can also see it from this distance. You actually get to see a very strong effect of the gravitational lensing that is created by this supermassive object. Now, one thing I forgot to mention is the size of this black hole. The way we measure black holes is usually with something called Schwarzschild radius, which refers to the, I'm gonna come close to it so I can show you, the radius of this right here. So this is what we call event horizon. This is the area where we don't really know what happens after. Like, nothing actually leaves event horizon, even light cannot escape it. And on this radius right here, this is where escape velocity is basically equal to the speed of light. It's close to 300,000 kilometers per second. And so this radius from the center to here is approximately 12 million kilometers. So that's about 1/4 of the orbit of Mercury, or about 17 times the radius of our sun. So it's not very large, but at the same time it is very, very massive, and it is obviously a very scary and a very powerful object. So there's a lot of energy involved here, and there's definitely a lot of things going on that we are not even certain about yet, because this is essentially what our entire galaxy orbits around. And so, all in all, this is actually a pretty awesome object. I mean, it's actually so awesome that I'm really surprised we don't have a better name for it yet. And unfortunately, because this object actually has no cool name yet, I think one of the better names for it would be Kronos. Kronos is, of course, the elder god in Greek mythology who is known for eating his own children. And is actually a very famous painting that depicts him eating his own child. And it obviously also means time. It also represents time. And I think it's a pretty good description, or a pretty good analogy to what a black hole is. And we're going to come really, really slowly to it, so you get to see how everything changes as we come closer to it. But if you actually have a much better or much cooler sounding name that is relevant to Greek or Roman mythology, because it's the astronomical convention, it has to be from one of the mythologies. It can be Norse mythology, it can be Slavic mythology, it can be any kind of mythology, but it has to be a deity or a god that is basically from one of those mythologies. And if you have a really cool name that sort of applies to a black hole, and as we're basically approaching event horizon, this is how everything around us will change. But yeah, post it in the comments below, please, and thank you. And obviously, I'm not sure if one day someone will actually name it that, but you never know, because people are watching this channel and maybe they'll like our idea. Anyway, so do post your suggestions in the comment box, and as we land on the event horizon, you'll actually get to see what you would see if you were to approach a black hole really, really slowly and then land inside of it. And what happens after is anyone's guess. That's probably one of the mysteries we still haven't been able to resolve even today. Anyway, I hope you enjoyed this video, and I hope you learned something about the black hole in the center of our galaxy. And as we land on it, you'll notice that we started orbiting really, really fast. I'm actually going to slow down time now, because what's happening now is that the black hole is spinning really fast. And because it's spinning, you get to see these really, really crazy effects on the surface of this black hole. And so hopefully in the last video, I was able to kind of explain to you what exactly black holes are. Essentially, these are objects that create such a massive mass that space starts to fold on itself, and nothing can actually escape them. So this is essentially what a black hole is. Now, if you approach this really closely, you'll actually start even witnessing what's known as blue shift effect in space engine, and this is actually right above the event horizon. This is what the universe would look like here. And then as you enter the black hole, obviously things start disappearing behind you. But that's not what we're talking about today. What we are talking about is how do we actually see them. Light cannot escape them. They're very, very dark, very, very black. So why do we even know that they exist? And the first answer to that is pretty obvious. You can kind of see the lensing effect in the back there. And that's essentially what helped us find at least some of the black holes. There's actually quite a lot of images you can find online from NASA and from other space agencies that have discovered these lensing effects from what seems to be empty space. Now, there are two candidates for this empty space. One of them is dark matter, but the other one, the more obvious, black hole. So lensing effect, basically the effect of the mass in the center right here that essentially bends the light as it passes close to it, is one of the ways that we can actually see them. This is essentially how we normally find them, or used to find them, until we've discovered a few more methods. But these lensing effects are not always very obvious. As a matter of fact, you have to actually look really closely into the empty space to even observe them. So there are actually a few more methods, and one of them is a little bit more interesting. This is essentially how we've discovered objects known as quasars and blazars, because we've realized that many black holes, not all black holes, but many of the black holes, have something known as the accretion disk. I'm going to come to the central black hole in the middle of our galaxy here, too much, and show you what accretion disk is if you have never actually heard of it or never seen it before. So this disk around this black hole is essentially formed by various matter that the black hole tried to absorb, most likely stars that passed by too close and were basically sucked in or disintegrated. And a lot of this is essentially material that eventually either falls back into the black hole, or falls into the black hole that is, or is being thrown out with these two jets that you don't really see here, but there's these two massive jets of very highly radiated particles that are essentially projected into two directions. And we know that our galaxy has a black hole in the middle that does that, and pretty much every galaxy out there has one as well. And these jets, if they point directly at us, are a telltale sign that there's actually a black hole pointing at us. Now, our galaxy doesn't produce these jets into our direction, so we don't really know much about them, but we know that they are there, and we can also, if we actually look carefully enough, can also detect the projections from the accretion disk as well. So all of this is visible light or X-ray or gamma ray radiation, and the two jets that the black hole creates are very bright. So some of the farthest objects in our universe, so if I were to actually leave our galaxy and go really far away, where we're basically leaving closer to the end of the universe, or visible universe that is, some of these really far away objects are actually pointing at us with those specific rays, with those specific jets, and we can actually see them even from something like 13 billion light years away. So that's how bright these rays are, and this is essentially the second method for us to detect these black holes, or actually many different black holes. And so, for example, these two bright galaxies may actually have a black hole jet pointing at us, which is why they're so much brighter than other galaxies that you see in the back. And let's actually approach a completely different galaxy and try to look for a black hole in there, so I can actually show you, or try to explain to you, the third way that we use to find various black holes. And this is actually a method that was theoretical until recently, until we were able to show it experimentally in the lab as well. And so here I am next to some other randomly generated or procedurally generated black hole in a completely different galaxy far away from home. And what we're going to take a look at is this theoretical method known as Hawking radiation. So let me just try to kind of explain to you by approaching very close to the event horizon. So every second, or basically always, there's particles that are being created and destroyed in our universe. When these particles are created, and this is actually the principle of quantum mechanics, they create, let's just say, a proton and antiproton. So in other words, matter and antimatter. But at the same time, when these particles are created, normally if they're close enough, and usually they are close enough, they're instantly destroyed and might produce some energy. This happens everywhere, this happens all the time. But if it actually happens right here, if it happens on the event horizon with one of the particles being produced on the inside and one of the antiparticles on the outside, or vice versa, antiparticle-particle, the particle that's inside the event horizon is actually going to fall into the black hole. But the other particle, the antiparticle, is going to escape and eventually produce something that we refer to as Hawking radiation. It's sort of a very low frequency light or specifically radiation, that is then released from the event horizon and essentially is spread across the universe, which we can technically detect. Now, we haven't really been really certain about this until very recently, when an experiment using sound waves showed that this is actually possible with wave radiation, that is. And so this experiment kind of theoretically showed that if this happens with sound waves, it's very likely going to happen with light waves as well. So it's very possible for this radiation to actually exist. But the problem is we would not be able to detect it from a larger black hole like Sagittarius A, which is at the center of our galaxy, because unfortunately Sagittarius A produces way too much other radiation, so it's going to basically overshadow it. But a small black hole like this, specifically a black hole that's only a few masses of the sun, and I think this one here is only 9.8 masses of the sun, this would produce a lot of Hawking radiation because it would be dissipating or essentially evaporating a lot faster. And what happens when this radiation is produced is that essentially black hole loses its own mass. So a particle on the inside falls in, but the particle on the outside falls out, and that takes away energy and of course mass from the black hole. So theoretically, after billions of years, any black hole is actually going to dissipate into nothingness and disappear completely. Now, even though we actually haven't technically seen this radiation just yet, there were some unofficial potential observations. Like, for example, in 2010, there might have been an observation of what seems to be Hawking radiation from one of the smaller black holes. And we also tried to use Fermi's Space Telescope to try to discover if we can see these primordial black holes, for example, that would actually emit quite a lot of radiation. But so far, no luck. So far, we were only able to represent this, or I guess recreate this, using sound waves on our planet Earth. But of course, theoretically, this should also apply to black holes as well, meaning that maybe, just maybe, this is actually the most efficient way for us to see black holes directly, because this light, this Hawking radiation, would be coming directly from the event horizon and from the surface of the black hole. And so essentially this is the third method that we have today for detecting these unusual, mysterious objects, and hopefully one day we'll be able to not only see them, but possibly even visit one as well, similarly to the movie Interstellar. Anyway, so that's all I wanted to say about black holes in this video, and hopefully now you know the 3 ways that we detect black holes and how we can actually see them in outer space. Thank you so much for watching, and if you still haven't subscribed, don't forget to subscribe, and don't forget to share this video with your friends. Hello wonderful person, this is Anton, and in today's video I wanted to redo my challenge where I tried to find the central black hole in the middle of our galaxy, but this time using it the smart way, because many of you have basically told me that I had something very important disabled under settings here, which of course is the clusters. Now, for some reason in my version of the game, this was disabled by default, so I didn't really get to see the clusters, which make it so much easier to find the central black hole known as Sagittarius A. If you still haven't subscribed, click that subscribe button right now, because today we're going to talk about something that will teach you about globular clusters, and many more videos will come that will teach you even more. Welcome to What the Math. And so here we are next to our moon, and we're going to go on an adventure and try to once again discover the central black hole in the middle of our galaxy. But what I'm going to use this time to find it is essentially known as a globular cluster. What are these clusters? Well, you're going to see quite a lot of them as soon as I turn around here and start moving across our galaxy closer to the center. You're actually going to see quite a few. And many of them are so bright that we used to think that they were just stars, but turns out that they're actually globular clusters very, very far away. Some of the more famous ones are, I believe there's this really famous one that you can actually see with your naked eye, known as Omega Centauri. Oh, here's actually one of the clusters right there. And that's a nebula. There might be some more coming up really soon. But basically, these are essentially stars. There's another one right there. These are essentially stars, thousands and millions of stars all together. Let's go take a look at one. That are orbiting in a similar fashion. They're basically orbiting all together. There was a speculation that there might be an intermediate massive black hole inside, but turns out that we might have been wrong about this. So maybe, just maybe, there are some black holes, but they're not actually orbiting around a black hole at all. As a matter of fact, these stars here in this globular cluster might be just kind of sticking to each other, sticking together using their own gravity. So that's basically how, or what is the best way to find the central black hole Sagittarius A in the middle of our galaxy, because it just so happens that, at least in Space Engine, one of these globular clusters contains the Sagittarius A. We're going to accelerate time here a little bit just so we can actually see the orbits of the stars that are going to be orbiting around the supermassive black hole. Okay, now where exactly are we going? Oh, okay, here we go. I think we're going to the center of the galaxy first, and we're going to look for one of these globular clusters. Now, most of these are usually about 10 to 30 light years in size. They're not actually very, very big, but as you can see, there's so many of them in the center here. Now, let's see if this is the one, maybe. And the interesting part about these things is that they almost always contain ridiculously ancient stars. All of these stars are super old. These are actually possibly the oldest stars in the universe. Or at least some of the oldest stars in the universe, and most of them were actually born only hundreds of millions of years after the creation of the universe. So a lot of these stars are basically close to 13 billion years old. Now, am I in the center? I think I am. Maybe it's this one. Maybe it's this one. Oh, maybe it's that one. Let's check it out. I'm sure we'll find it eventually. It's a lot easier if you're actually just looking for a moving object inside a globular cluster, because that's essentially how I should be looking for the supermassive black hole in the center of our universe. But you know what, the way I found it before was a lot more fun. It was a lot less practical, but it was more entertaining because I basically flew around the galaxy looking for a needle in a haystack. Alright, so maybe it's here somewhere? Maybe, just maybe? Nope, not here. Nothing is moving. No motion detected. Unless I accelerate time, which would actually show it to me a lot easier. Anyway, so let's actually talk a little bit more about these globular clusters. I think the really interesting thing about them is that they often contain really, really bright blue stars, or white blue stars, known as blue stragglers, and these we believe are formed when two of these stars within a globular cluster actually basically combine. They collide into one another and they create a more massive star. So if you see a star that's more bright here, like for example, if I actually decrease the brightness, the brighter stars might have actually been created by a collision of two stars, because a lot of these stars are very, very close together. So imagine you were actually, let's go back to this. Imagine you were actually like living on one of the planets in one of these stars here. Your sky would look incredible. So we're gonna zoom in here. Let's actually zoom in. So imagine this is a planet you're on. If you look into the sky, you would see a lot of beautiful brightness, a lot of really, really cool things. It's very, very gorgeous things. Yeah, so these globular clusters, there's quite a lot of them. There's actually over 100 of them in our galaxy, Milky Way, and some galaxies, especially supermassive galaxies, contain several thousands of them, and each of them contains millions of stars. So it's quite a lot of really interesting stuff going on there. Alright, I'm not actually having luck here finding the supermassive black hole, but it's probably because I'm not even trying. I'm not actually even looking for it, to be honest. I'm just flying around trying to show you, or trying to teach you about these beautiful creations known as globular clusters. But I actually have a strong feeling that I just didn't see it. It's gotta be somewhere in this one. It has to be somewhere in here. Isn't it somewhere in here? Maybe not. Maybe I was wrong. Huh. Well, because that looks like we're right in the center, right? Anyway, let's move on. Let's move on to the next one. Let's move around. Let's find another one. Another one of these globular clusters. Now, the majority of stars in these globular clusters, as I mentioned before, are very old. So there's quite a lot of white dwarfs in here. Basically, this is what our sun will become one day. And there's also quite a lot of other ancient stars, such as yellow and red stars, that are just more massive than our sun, but are definitely very, very ancient. And they look very different from what we have in our own neighborhood, close to our sun. But nevertheless, though, because these stars are so ancient, this would be a very interesting place to investigate and to learn about our universe, because many of these globular clusters contain a huge amount of really, really ancient matter. Really, really old stuff. Stuff that's so old that's probably as old as our own galaxy. And many of these clusters were actually captured from other galaxies that a long time ago passed very close to our Milky Way and basically had some of their stuff either stolen or were completely destroyed by the Milky Way. And so many of these globular clusters actually came from the outside of our Milky Way. Alright, so I still don't see anything, but I'm sure it's gotta be somewhere nearby. I have this feeling that it's somewhere here. Alright, let's go to the next one and see what we can find there. Although, maybe, just maybe, this kind of looks familiar. But, yeah, there it is. There's the motion. I don't even know how I didn't see this before. There you are, my beautiful. Sagittarius A. Welcome, everyone. This is Sagittarius A. So, as you can see, it's right in the middle of the globular cluster. And we know that this is the central black hole because of the amount of stuff that's moving around it. I can actually now successfully zoom into it, and let's approach it really, really, really slowly. Anyway, so that's what these globular clusters are all about. Definitely still a lot of mystery about them. We don't really know how they were formed or when exactly they were formed, but it's very likely that many of these stars that are in these globular clusters, including the black holes that might be in there, and there's actually the black hole. If you haven't seen it yet, this is it. There you go. Anyway, so essentially, yeah, so these globular clusters are everywhere, and they're quite important. They contain a lot of mass and obviously a lot of mysteries as well. And as I mentioned before, the so-called blue stragglers, the super bright stars that you kind of see right here, are essentially, or we think are essentially formed by a combination of two different stars. And this is something we're going to explore in one of the future videos. But in the meanwhile, since we found Sagittarius A, let's just go in and make this universe end. Now, where is it? There you are. This is the end of the universe. Say goodbye, everyone. We're going to go backwards. Bye-bye. And I totally missed. One more time. And here we go. Thank you for watching. I'll see you guys in the next video. Game you later. It's so dark in here. Bye-bye. Now, I'm actually in Space Engine right now, and I have found a black hole very close to our planet, and this is actually the effects that Space Engine creates when you approach a black hole. And today I wanted to actually kind of explain to you what exactly has been found by the researchers, and also give you a better visual understanding of what it means and how it may affect our future understanding of the world, and of course, how it may actually change our understanding of physics, astronomy, and so on and so forth. So, first and foremost, let's actually briefly talk about who those people are and who actually is responsible for this big discovery. And as I'm trying to escape the black hole, I think I'm actually stuck here. Maybe not. There we go. We're escaping the black hole and flying into outer space. And so the actual team is called LIGO. This is short for Laser Interferometer Gravitational Wave Observatory, which is basically responsible for finding these so-called gravitational waves, which were a prediction of Albert Einstein almost exactly 101 years ago. He actually said there was something called gravitational waves, and he wasn't even sure if they're real or not, but he said that they're very likely to exist, but we may not be able to ever see them because they would not be actually very prominent. And so what this infers is that, so in space, in space-time specifically, once in a while you'll get ripples of gravity and time and everything And these ripples are usually the effect of either two black holes colliding or neutron stars colliding, or something that is very, very, very dramatic and massive that happens on the space scale, on the astronomical scale, and then causes these gravitational ripples. And he said that these ripples were sort of the effect of his special theory and general theory of relativity, specifically actually general relativity. And this was one of the last, if not the last, predictions that he made that was still not officially proven. And we have now officially proven all of his theories, and so now that also means that Einstein was 100% correct in his predictions. Anyway, so before we talk more about this, let's actually escape our galaxy for a second into the outer universe, because I wanted to show you what has been detected. So last year, sometime, I think it was August of 2015, just when this LIGO apparatus, which is actually a very big machine consisting of these detectors that are over 3 miles long, and there's actually 2 of them in the US. As soon as it was turned on, almost exactly within like this, 24-hour period, the scientists detected an anomaly, or not really an anomaly, but what they were actually looking for. And this was a collision of 2 black holes, approximately 1 billion light years away from us. So what I'm gonna do right now is show you the scale that we're talking about here. And this is, of course, billion years ago as well. So this is a noise that we've detected that is very, very old and very, very far away from us. So literally a long, long time ago in a galaxy far, far away. And we're still not there. We're only about a third way there. So this is where... so I'm just going to give you an idea of a distance we're talking about here. So right about somewhere around here. So somewhere in this region, this is exactly 1 billion light years away from us. In one of these other galaxies, there was a collision of 2 black holes. So let's just like pick a random galaxy here and go to object. And somewhere inside, if we actually fly inside this galaxy, and then go inside, right in the middle, and then go into the search here, not this search, other search, and now look for a black hole within 100 light years of us. And just to look at, there's a binary black hole possibly, black hole binary, there we go. So it was a binary black hole where 2 black holes, as they basically orbit around each other, they approach each other, and at some point they collide. So I don't think this is actually a binary black hole. I think this is possibly... Oh boy, this is a big system. Not exactly what I was looking for. I was just looking for... Yeah, this is a black hole, and I believe... is this what I think it is? I think it's a brown dwarf. Yep, it's a brown dwarf. Let's see if we can actually... No, we unfortunately can't really find a black hole in this environment. It's a little bit too small. But we can definitely find this one. This is going to be a little bit easier. This is a singular black hole. And basically, yeah, so in this particular space and time, so there were 2 black holes orbiting around each other. Now, I'm going to demonstrate this in Universe Sandbox 2 in a few minutes. And as they basically approach each other closer and closer, at some point, they start orbiting each other so fast... and we're talking about several times per second. And this is something I'm going to help you visualize with the Universe Sandbox. And then they collide, and this is when the noise stops. And the noise we're talking about here is, of course, the gravitational ripples. So every time they orbit, they create a ripple. The more they orbit, the more ripples they create. And if they create several ripples per second, this is something that we can actually then convert to sound. And this is actually the sound that is technically audible to us. We can actually hear it in audio waves, because this sound is something that is representative of these gravitational waves, but in something that we can actually understand. Anyway, so let's go into Universe Sandbox, and I'm going to show you more and explain more about this. And here we go. So we have 2 black holes orbiting around each other relatively fast. This is actually real time, 1 second per second. And the 2 black holes that we detected, or I guess they detected, they were 36 times mass of Sun and 29 times mass of Sun. So they were relatively similar in size to each other. And basically they were orbiting around one another and creating these ripples that unfortunately it's going to be really almost impossible to simulate them, but this is what the picture of all of this looks like if you were to actually look at it. And with time, these black holes would actually move closer and closer to one another. So we're going to actually simulate that as well by, well, let's actually just decrease their total velocity until they start moving toward each other a little bit more. So there we go, they're a little bit closer now, and they're basically creating a one ripple every time they pass by. So one ripple and two ripple, and so these ripples would accelerate the closer they get to each other. So if I were to change this to 5,000 now, and this is going to be, let's just say 7,000, they would now approach even closer, and there you go, they're orbiting a lot faster now and creating even more ripples. And basically with time, they would approach so close to each other that they would essentially collide into one another. And so, and right before the collision, and I'm gonna have to decelerate this even more because they're just going crazy here. This is actually slow motion now. And so with time, at some point, they will actually combine into one. And there we go. So this is almost the collision. You can kind of see them exploding. And basically at this moment, this is when the sound stops. And by sound, I mean the actual ripples. The ripples stop. And this becomes one massive black hole. So the black hole that this created was approximately 62 times masses of sun, meaning that 3 masses of sun was the energy released from this collision. So the actual energy released at the end, when the black holes actually finally combined into one another, was so massive that it was actually equivalent to 3 masses of sun in terms of energy. It's actually a huge amount of energy. And this is essentially another Einstein's famous formula, E equals mc squared. So energy here was 3 masses of sun multiplied by speed of light to the power of 2. And if you ever do the math behind it, you'll realize how ridiculously high the energy was. Alright, they're still kind of orbiting around one another, so I'm gonna try to finally combine them. Let's actually decrease the speed until they finally come into one. Oh, they just don't want to do that. And what I just realized right before they actually combine into one, I think the bigger black hole actually managed to absorb a lot of the mass from the smaller black hole, because the smaller black hole was much smaller than before, which is actually pretty interesting. I'm not sure if this is how exactly it happened, probably not, but it's interesting how this game is actually able to recreate this. Now, like I mentioned before, so it lost 3 masses of sun, so technically there should be 62. And the other masses of sun were released as pure energy. And what you're observing here, the actual little yellow fragments, that's basically the explosions from extra mass that collided with this black hole. It would not be like this at all. This is actually not very realistic, but it does create this really cool effect. It kind of almost looks like an eye if you look at it from a certain angle. And there you go. This is our black hole eye. This is probably going to be the screenshot for this particular video. Now, the interesting thing is that what this allows us to do now is not only to use telescopes to see things, but to actually literally hear things. We finally discovered the astronomical ears to be able to hear all of these collisions, all of these really cool astronomical events that were otherwise invisible to us. And specifically, this will also allow us to finally study gravity in more detail, and will very likely explain a lot about gravity that we didn't really know before. And of course, this also might one day lead us to discovering things like anti-gravity or possible anti-gravity drive. So there's a lot of potentials and possibilities that will actually stem from this amazing discovery of the collision of these 2 black holes. And I think one of the more important reasons behind this discovery is, of course, the fact that we are now actually able to detect these ripples. Before, these ripples were kind of invisible to us. We would never be able to even see them, because basically space-time, even though we're in it, is impossible to actually feel and detect. When the space stretches, you don't really feel it. But this LIGO machine thingamajiggy, along with the fact that we now have a very specific technique to measure ripples of space and time, will allow us to actually literally feel the space. We can now hear it, we can hear it stretch, we can detect things that were invisible to us. And since scientists have been actually looking for this for over 40 years now, I think it's probably one of the biggest discoveries of, I would say this century, but the century is still young, so possibly the last few decades. Definitely one of the bigger discoveries. Now, so this is what I wanted to show you, what I wanted to explain, and I also wanted to actually let you hear the sound that the collision of these two black holes created. So this is actually the sound itself. And of course, this is the reinterpretation and reimagining of the gravitational ripples in terms of sound. And I think before we finish this video, let's actually possibly add a few more black holes in here and create some more ripples and more explosions of black hole proportions, which is going to put them as still, and they'll start colliding into the main black hole here. Hopefully, or not, or maybe they'll just fly away. But every time the black hole or any kind of a massive body, including neutron stars. Oh no, my black hole disappeared. I don't know what just happened, but it's gone now. Every time a massive body like a black hole or neutron star actually comes close to one another, or like for example right here we have two of them orbiting around each other, they'll be creating these ripples that can then be detected with this new technique that we now have. Actually, it's not a new technique, but it's a technique that has finally been proven to actually work. And there's a lot of new laboratories around the world that started to actually create their own machines now, but because they're so expensive and so large, it might be a while before other labs are able to actually detect gravitational waves as well. Anyway, I hope this video was kind of clear, and I hope I helped you visualize this important discovery that you've probably heard about on the news or possibly read on the internet. And this was the discovery from February 11th, 2016, and will very likely change our understanding of the universe. And so in today's video, what we're going to be doing is going on a bit of a trip. So right now we are near Earth, but we're actually going to go about 60 million light years away from our beautiful planet to a galaxy known as NGC 1365. So I'm going to go in here, type NGC 1365. We're going to lock our location or our destination. And first of all, let's actually take a look at it. So in Space Engine, it's about 56 million light years away. It is right there. We can't really see it because it's really far away from us. So we're just going to go and zoom to it, and you're going to see it in a second. So it is pretty far away from us, but why we're going here is an interesting reason actually. So we've discovered very recently by studying various gravitational anomalies around this central black hole right in the middle of this galaxy, is what we've discovered about it is that it's actually very similar to the supermassive black hole from the movie Interstellar. As a matter of fact, it is almost exactly identical to it in the way that it bends time around it. So we're actually going to go and find it right now, because it doesn't actually display in this game by itself. We do have to find it first. And we're going to go into the center of this galaxy and take a look at it as well. So what exactly am I talking about when I mean it's actually very similar to Interstellar? Well, what I mean by this is that it actually slows down time around it to the extreme. So if you ever watched Interstellar, you may remember that on one of the planets where they land, the time is so slow, or I guess it moves so slow that by the time they come back to their spacecraft, something like over 20 years passed, even though they were only for about 2 hours on that particular planet. Well, this is actually exactly what's happening around this black hole as well, that we're actually approaching relatively fast, but I think I just missed it, because I think it's located somewhere in this globular cluster right there. So let's actually go there. And as I'm approaching this globular cluster, let me try to explain to you why this is happening. So the black hole in Interstellar was actually not just very supermassive, but it was also spinning. As a matter of fact, it was spinning very, 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 very fast. And once we find this black hole, I'm going to kind of try to demonstrate to you what is happening when the black hole spins, because that is essentially how it was able to slow down time so dramatically. 1 hour on that particular black hole was several years in reality. And when I say reality, I mean, of course, our space-time. All right, we missed it again, so let's go back. And here we go, we're going to be entering this very, very slowly and try to look for something that looks like a black hole. Now, to see this black hole, I'm going to actually accelerate time, and we're going to be looking for spinning objects, specifically stars orbiting around some kind of an imaginary location in space. And the way we're going to find this is by basically approaching a location where my pointer is pointing, and even if it hasn't appeared yet, it should appear any second now, because the game sometimes doesn't actually render black holes right away, but it does render them when you approach them close enough. So it's going to appear any second now, and we're going to actually see what this supermassive black hole looks like. And I think it might actually be somewhere right there. I see something spinning, or possibly something really, really bright. So maybe it's somewhere in this location right here. So we're going to move a little bit closer to this part, and it's very, very close to us. Oh yeah, it's definitely this. I think we found it. I think this bright spot in the middle is that supermassive black hole. So we're going to slowly inch our way toward it, and look at that. Suddenly it appears in front of us. So there you go. So that is the supermassive black hole in the middle of this galaxy. I'm going to slow down time just a little bit. It has quite a lot of stars orbiting around it. Let's see how many. Ooh, look at that. So many. All right. We're going to go closer to it. Let's just move a little bit closer so you can actually see what's happening in the middle. And as we're moving closer and closer, you'll notice that things get a little bit more hectic, a little bit more bright. There's also some really interesting visual effects that you can see right there. The actual lensing effect caused by the supermassive black hole. And the stars that orbit around it move really, really fast when they get close to the actual black hole, because that's their periapsis of their orbit. But this black hole is surprisingly bright. This black hole is actually a lot brighter than I thought it would be. Now I'm going to slow down time just a little bit more, and we're going to approach it even more. So there we go. So there it is. Now this is the accretion disk, and I'm inching my way toward the actual black hole because I want to show you something. So this particular black hole is spinning. It's spinning really, really fast, actually in this opposite direction, spinning really, really fast. And as a matter of fact, the scientists have discovered that it spins at almost the speed of light. So the tip right here, this part, is moving almost at the speed of light, almost at 300,000 kilometers per second, basically pushing the limits of relativity. It's as fast as a black hole can actually spin. And because it's spinning so fast, the entire space-time around it, and I'm not just talking about the accretion disk, but I'm talking about the actual space-time around it, sort of folds and bends and spins with it really, really, really fast. So the space-time right next to it spins at close to speed of light. A little bit farther away, it spins a little bit slower. A little bit farther away, a little bit slower. But even at this distance, it spins really, really, really fast. So all of this accretion disk material experiences different time flow. Basically, what's really close to it moves really, really, really slow in comparison to something that's right here. I guess the best example I can give you is, imagine a particle that only lives for about 1 second. So maybe there's a particle that just lives for 1 second and then disappears. So if I were to put this particle far away from this black hole, somewhere right here, maybe it would live for about 1.5 seconds or something. If we move a little bit closer here, it will live for about 2 seconds. A little bit closer here, maybe 4 seconds, 8 seconds, 16 seconds, and so on, until we get very close to it, and it would actually live for several hours. Because even though for the particle itself, in its time frame, the time doesn't actually change, so basically the particle itself just sees its life as 1 second, we from this distance would see it as living several hours. It would actually be moving in slow motion to us. Because the dragging of space-time slows down time dramatically, up to the point where it might actually be some of the slowest time in our universe. So essentially, if you were to take two twins, brother and a brother, who are exactly the same age, and then you were to leave one of them on Earth, and then you were to bring one of them, and there's actually two astronauts that I'm showing you on the screen right now that actually are twins, and you were to put one of them orbiting around this black hole right here. And because this is actually supermassive, he would not be killed, he would not be spaghettified, but he would just be orbiting around it. And then if this astronaut that's orbiting around the black hole would stay there for about 1 hour or 2 hours, and then somehow come back to Earth, he would realize that it's very likely that everyone he knows, including his twin brother, has already been gone. They're essentially dead. And that's mostly because for him only an hour or two passed, but for people on Earth many years have passed, and this is what we actually call relativity, and what we actually refer to as time dilation. And the effects of time dilation right next to this black hole, right at the edge, are absolutely extreme. And of course, you could also obviously use this effect to essentially time travel. So if you were to actually stay here for, you know, several hours, several days, several weeks, and then come back to Earth, you would be moving in time. You would be moving through time, and you would be arriving to Earth into the future. And for you, only a few hours or a few days, a few weeks have passed. But for people on Earth, many years and many decades, and possibly even millennia have actually passed. Now, let's actually take a look at some of these stars here. Specifically, I think this one right here, because it is the star that approaches this particular black hole the closest. As a matter of fact, right when it's the closest to this black hole, I think it's going to be there right around here. This is where we're basically the closest. So for this particular star, time also obviously passes a lot slower when it's at the closest to the black hole. So this star would actually have really interesting effects on it. First of all, because it has quite an elliptical orbit, sometimes it's close to the black hole, sometimes it's far away. Which also suggests that basically this star and all of the particles in it kind of go through really different time frames every once in a while. So here specifically we're talking about something like every year, or 324 days. Every 324 days, it goes through some really interesting effects. So basically it slows down quite dramatically right here for an observer from the outside, and then it moves away from this black hole and starts moving at a slightly different speed again, or a slightly different time frame, that is. So right here it's very slow, and now that it's going to start moving away from this black hole, which it's doing right now, the time would start accelerating, and the star would start basically spinning a little bit faster and doing things a little bit faster, and all of the particles on the inside would also act a little bit faster. But this is actually a very interesting system to observe, and this will be a very interesting black hole to study, because this is essentially how we could learn more about the universe, by studying these very interesting time dilation effects. And obviously experiment with things that were actually seen in the movie Interstellar, because all of those effects that you saw in Interstellar, all of those time dilation effects and time travel effects, are essentially real in this particular galaxy. Now obviously these effects would disappear if you were to move away quite far away from this black hole, but being so close to it, the effects would be very dramatic. So even for this star, or for any of the other stars orbiting around it, these effects would be quite dramatic, and they would actually experience quite a long life in comparison to other stars in our universe, because the closest star, or some of these closest stars here, would actually live several times longer than any other star in our universe because of the time dilation. So even though our sun might only live about 10 to about 12 billion years, this star right here that I'm pointing at right now, even though it's very sun-like, would actually live much longer, at least in relation to obviously our sun, and from the perspective of our own solar system and our planet Earth. So this star would maybe live 3, 4, 5 times longer, basically surviving for many more billions of years than our own sun. And well, anyway, so that's really all I wanted to kind of show you in this relatively short video. And I just wanted to kind of explain to you that sometimes things that you see in science fiction are actually real. They're reality. They're basically based on things that do exist in the universe. So many people may have not realized that Interstellar, even though it's actually a science fiction movie, was actually showing you something that does exist in real life. And specifically, we're talking about this particular supermassive black hole known as NGC 1365. And before we end this video, let's actually enter this black hole and end our video inside of it. Because this is a very beautiful black hole that I kind of wanted to explore on the inside as well. And anyway, thank you so much for watching, and hopefully you learned something from this video, and hopefully you enjoyed watching it as well. And if you have and you still haven't subscribed, click that subscribe button right now, because there's so many more videos coming in the future. And thank you so much for watching. Please share this video with someone who you think might learn something from it. And if you still haven't seen Interstellar, go check it out. It's an amazing movie that will teach you quite a lot about our nature, science, universe, and obviously space as well. So we're entering the supermassive black hole. Everything is going to blue shift to the extreme, and the universe behind us is going to close forever. And that's the end of the universe. Thank you for watching, I'll see you guys later, game you later, and as always, bye bye. And now let's go back to Earth. And what you're looking at right here is a slightly darker version of this binary system. So this is essentially the system known as Cygnus X3. It's one of the brightest X-ray sources in our galaxy. It's basically a source of mystery for many scientists because some of these emissions are so powerful that we don't really even know what is actually going on here, but we have some ideas. Now, if you guessed that this is a black hole, you're not entirely correct because this is actually not a black hole. This right here, in what you see in the background, I'm going to actually zoom out for a second just to show you how large this object is and also possibly return the luminosity to its original value. So close your eyes for a second and boom, it's super bright. This is a Wolf-Rayet star. Wolf-Rayet star is an extremely enormous type of a star that is very, very unstable as well. And I've talked about this concept previously. You can check out some of the previous videos where I actually described specifically what this actually is. But this Wolf-Rayet star has this very, very, very compact and dense object that is very likely to be a neutron star orbiting around it every 4 or almost 5 hours. So one orbit here is actually very, very, very fast. It's 4 hours and 47 minutes. If I were to accelerate time, you would see how fast it is just by looking at this sort of an animation. So there you go. So this is the Wolf-Rayet star, and this is the potentially a neutron star that orbits around it. Now, as you can see, if you can kind of look closer, the actual larger star, it's sort of attracted to this neutron star. Not attracted per se, but it's actually tidally locked to it. And the neutron star is currently absorbing quite a lot of various mass and material from this large star, and basically is stealing most of it and is creating a lot of various energy from it. If I were to actually look at the mass of this right now, it's close to about 39 masses of our sun. Whereas this neutron star is only about 2.5 masses of sun, but it's constantly eating up a lot of the mass from the star, and it kind of sort of creates a very, very unusual teardrop-like shape that possibly is sort of coming out of here and is dragged inside of the neutron star and then creates the accretion disk around it that you'll see in a second as soon as I zoom into it. And you'll see accretion disk orbiting around it, which is basically created by the absorption of the material from the Wolf-Rayet star near it. And so, notice how small this object actually is in comparison to the Wolf-Rayet star. This is how tiny it is. And there is the accretion disk orbiting around it, and there is that humongous Wolf-Rayet star in the background. Now, the interesting thing about this particular object, and I'm actually going to slow down time here a little bit just so you can see the accretion disk in more detail, is that, well, first of all, we've detected some of the most powerful emissions from here. So this is what actually is going on here. This is the neutron star, very, very dense, very bright object that is actually going to create quite a lot of interesting effects if I try to land on it. So there is the universe and the galaxy as it appears from the surface of this neutron star. It actually is all squished and condensed and basically curved into one little window. This is essentially what it would look like if we were to stand here. And this is with an actual luminosity, and you can see everything is actually blue shifted because the space-time curvature here is so dramatic that basically not only is the time frame here is very different, and basically you're technically traveling through time if you're standing on the surface here, but you also get to experience very unusual Doppler effects, and of course the entire universe is essentially a small window. So you actually don't even see the world in 3 dimensions. You just kind of see the small window around you. But anyway, so what exactly would we classify this object as? Well, it's technically classified as a micro quasar. Quasars are a concept I've covered previously as well. You can check them out in one of the previous videos. But This microquasar is called that because it's actually so energetic and so powerful that it produces just as many gamma rays, just as many X-rays that a quasar would, or basically a very, very active black hole that absorbs a lot of material and then spews it out from two directions, sort of up and down. And we're going to recreate this in Universe Sandbox in a second, but let's just look at this beauty in a little bit more detail in Space Engine first. Now, this is actually not the most famous Cygnus objects. The most famous Cygnus object I've talked about previously, it's called Cygnus X1. That is actually a black hole orbiting another very massive star. But this object, Cygnus X3, is more mysterious. As a matter of fact, some scientists think that it's not actually a neutron star, but might be something more theoretical, like a quark star, which we don't really know much about. It's a star that is not made up of neutrons, but made up of even smaller particles or subatomic particles known as quarks. But I guess what's really, really interesting about this is that this is actually one of the most luminous, one of the most brightest objects in our galaxy. This is why I had to decrease luminosity so much so that you can actually see it without going blind. It is so luminous, in fact, that we often see this over other objects, including, of course, many of the brightest large stars out there. And so essentially this is a very, very interesting, very unusual object. But what I wanted to do in this video, I actually wanted to see if we can recreate this from scratch, because this wasn't always a neutron star. This was once a large star that eventually went supernova and created this object. And so we're going to zoom out of here slowly, and we're going to move away from this system and then go into Universe Sandbox 2 and try to recreate this from scratch. So notice how tiny it is in comparison to this massive Wolf-Rayet star. It's just a little dot, a little speck right there. So anyway, let's slowly return its luminosity to its original value. Maybe increase the actual orbital speed as well. And here we go. Alright, so let's go to Universe Sandbox and recreate this. And so let's actually recreate this from scratch. We're going to go into stars here and add two really massive stars. Let's choose the biggest ones we have. Something that actually may seem like a Wolf-Rayet star, like for example Eta Carina B, and possibly a slightly smaller star that would very likely become a neutron star if it went supernova. Like for example, let's just go with Spica. So we're going to place them in orbit around one another. And here we're going to choose binary balanced motion orbit. Let's just place it right here. And I think maybe this is actually not close enough, or one of these stars is actually a little bit too large, because currently the orbit is about 2.18 days. So I'm going to have to decrease the size of this star, I think. And we're also going to rename these two stars. This is going to be Cygnus Partner, and this is basically Cygnus X3. So this is maybe a few million years ago, when both of them were very large stars. And then, for one reason or another, this star either lived off its life and went supernova, or possibly lost some of its mass and rubbed off against this star and basically went supernova. And what happened was this. So we're going to enable realistic mode here. And we're going to try to cause it to go supernova. So maybe if we do this, there we go. All right. Oh boy, it's too large. This is way too large. Here we go. So supernova has occurred. This was a few million years ago. It already has dissipated. So it's technically invisible to us. But what remained behind was what we would call a pulsar. So we're going to actually make pulsar from this. There you go. There's our pulsar. And we can possibly even change its orbit to make it orbit a little bit closer, although I think these parameters are already locked, so maybe we can't do that. So there is our pulsar, known as Cygnus X3. Now we're going to wait for this supernova to dissipate so that I can actually show you what is happening here. And we're also going to increase its magnetic field by about 10, because it's a very powerful pulsar. So let's wait a few thousand years. We're going to accelerate time here, making these guys orbit around one another. And with time, this supernova will actually dissipate and disappear completely. Although I just realized it's actually going to be really hard for me to wait for this to happen, because if I accelerate time a little bit more, all of this binary system will actually collapse and I'll probably end up losing both stars. So we might have to do this without making the supernova disappear, and just kind of go through the idea of what's actually happening here. So let's zoom into the system here. We're going to actually take a look at Cygnus itself in a little bit more detail. So this right here is the neutron star that you saw a few minutes ago in Space Engine. It's very, very, very bright, very, very powerful, very, very dense as well. Around it, there is going to be a kind of an accretion disk. Unfortunately, it's not present here, but we can actually manually create it by going into the ring system here and choosing a ring system with a few radii to orbit around this, right here. All right, so this didn't actually work for some reason. I think I'm pointing at the wrong object. Let's try this again. Maybe this will work. So maybe this actually has worked, but all right. So this seems to be some kind of a bug, because I was trying to create this ring, but unfortunately it flies away really, really fast, and I think it might be because of the supernova. Supernova might actually be dragging things out of the system right now, so this is why it's impossible to create anything that is stable. But anyway, let's just imagine there is actually a kind of accretion disk orbiting around this, and what we have, because of this accretion disk and because of the proximity to such a massive star, is essentially what you're going to see right here. So there is that accretion disk that I was able to kind of create finally, and there is that sort of a jet that is propulsed by the accretion disk and by the force of the neutron star, making this a very powerful pulsar. So these two jets that you see going up and down, this is what's essentially pointing at us, pointing at our planet Earth, and occasionally sends ridiculously powerful X-rays and ridiculously powerful gamma rays and so on and so forth. Now, it doesn't seem very powerful from here, but the reality is that it's such a powerful pulsar that I'm going to try to recreate it here. It is actually something like this big. It is causing a tremendous amount of energy to project toward our planet Earth, and some of it is some of the most energetic X-ray and gamma rays we have ever detected. So this is what happens once in a while. There's actually quite a lot of patterns we've discovered. There's one that's like about 370 days or so. Every 370 days there's actually a huge amount of energy that's released toward our planet, and we detected it with the various satellites. And so this object is known for these patterns. And they're also known for being extremely violent events. So violent, as a matter of fact, that it's kind of dangerous to basically be in that particular spot if they actually do occur, even though this object is something like 27,000 light years away from us. Or I believe it's actually 23,000 light years away. 27,000 is the other one called Cygnus X1. And so this is essentially how this object was created and what it actually does when it releases energy, and this is what it might look like from a distance. It's still very bright, even if you're really far away from it. Or might even be even brighter than that. Let's actually go into materials here and increase the total power of magnetic field to an even higher value of like something like 20. There we go. So even from a super far away distance, you'll still be able to see Cygnus X3 really well, specifically in X-ray and gamma ray wavelengths. And so all in all, this is actually a pretty fascinating object. There's quite a lot of mysteries about it, and this together is known as a high mass X-ray binary, because there's a binary system, there's a lot of mass involved, and it's definitely known for emitting a lot of X-rays, but also gamma rays. And one of the biggest mysteries of Cygnus X3 is that we still don't really know what it is. We don't really know if this is actually a neutron star, because some of the emissions we've received are so highly energetic that it might actually be something completely different, some kind of an exotic object we haven't studied yet, and possibly even a quark star. And so that's the essence of Cygnus X3 and its partner, known as V1521 Cygnus, and that's what it's all about. And so first, let's actually use Space Engine, because it does allow you to create this very beautiful lensing effect, and because it actually has a black hole at the center of our galaxy that I've showed you how to reach in one of the previous videos, that you can then explore in more detail. It's a supermassive black hole. In reality, it's about 4 1.1 million masses of sun, but this one here is only about, I think, 2 million. It's not as realistic, but that's okay. We'll forgive it. And the cool thing about this particular black hole is that it actually has several stars orbiting around it. Specifically, I think it's like 23 stars. And so we'll actually get to see some of the effects of approaching a black hole. But before I jumped into this black hole, let's actually define the ideas that we need to know about this. And specifically, let's actually define the idea of frame of reference. When you talk about black holes, you have to always consider the effects of general relativity. And here we're talking about the idea of the reference point. So there's actually two reference points when you're talking, or when you jump into a black hole. There's a reference point from the outside, where, you know, you're basically somewhere, let's just say on this star right here. And this is a star where one of your twins live. Let's just say your twin is Antonia, your sister, or my sister in that case. And then Anton, the adventurer, will actually try to enter the black hole. So you are somewhere around this system, and you're basically looking at what happens to Anton, your adventurer's brother, that tries to get inside of this scary looking dot in the middle. And of course, the second frame of reference is that of Anton. That is actually the reference where we are going to be flying inside of this black hole. So basically, we're going inside of it. And before your twin brother Anton actually lands or goes inside this black hole, let's actually debunk some of the myths about them. And I think the biggest myth here is that black holes are black. That's not entirely true, because they do emit something. They emit something called Hawking radiation, so technically there is a way to detect them. They also emit some other things like very, very low frequency radiation from all of the objects that actually do reach event horizon, and so there is a way to detect them, but just because they're so far away from us, it's very difficult for us to do directly. And misconception number 2 about black holes is that they are like vacuum cleaners. They suck everything into them. And that's not really true either, because just like stars, just like planets, they create gravitational effects. They basically bend space and time to such an effect that things kind of fall into them if they're too close, but they don't really suck anything in. If you were in a spaceship and if you were basically just using your engines, you would basically be able to, and if your spaceship is obviously very powerful, you would be able to easily just float above it. It's not going to suck anything in, just like a planet or a star wouldn't either. So you can technically orbit around black holes just like you would around normal star, but there is a point around black holes after which the actual orbit becomes kind of very difficult to achieve, especially if it's a very, very massive black hole. But we'll talk more about this later. And the myth number 3, I guess, would be not really a myth, but just misconception about black holes in general. I think most people think that, you know, as soon as you basically approach a black hole, you die. Well, that's not entirely true. First of all, it depends on the black hole size. And ironically, if it's a small black hole, if I were to look out there, and actually I do have some small black holes here already, if I were to go to one of these smaller black holes that I've discovered, like for example this one right here that also doesn't really have a name but just is called RS something something. So this black hole right here is relatively small. Its mass is about 8 masses of the sun. And so if I were to actually try to approach this black hole at a distance about this much, this is when the effects of gravity on me would be so high that I would actually be spaghettified. Here's a picture of what spaghettification looks like. Basically, the gravitational effects on, let's just say, the top of my head versus the top of, or the bottom of my feet would be so strong that I would be stretched into a spaghetti, my atoms would be stretched, and I would eventually just die. A horrible, horrible, stretchy death. That's, of course, if a black hole is small, and this would happen way, way before I would even reach some so-called event horizon that you see right here. Now, what about a large or mega super massive black hole like I was showing you in the beginning? A supermassive black hole, like the one in the center of our galaxy, would actually not have a similar effect. As a matter of fact, you can easily approach the event horizon, and you can even pass the event horizon without nothing really major happening to you. Okay, that's not entirely true. Something would happen to you, but nothing that would kill you. And that's actually where things get really interesting. So let's actually just take the frame of reference of Anton the Adventurer first, and we're going to try to enter the black hole. So let's just say you're in a spaceship and you're slowly approaching it. As soon as you start approaching it, you will start noticing really interesting things. Everything in front of you would start getting blue shifted. Basically, things would get more blue and blue, and I'll demonstrate this to you in the next video where I show you how blue shift looks. If I were to turn around, everything would be red shifted. It would start getting dimmer and dimmer and dimmer and dimmer and would become more red. And the other interesting thing about the approach toward the black hole is that, well, you obviously would see things getting bent just like you see here, and time around you would actually start to accelerate. You would start seeing things moving a little bit faster. I mean, increasing the time scale, and you'll actually get to see how some of it looks in a second. Now, this actually is better demonstrated by this video I'm showing you right now, and I posted the link where you can find a lot of these really cool simulations that are very realistic. This is what the actual approach would look like to a realistic black hole that has spin and has charge, and you actually get to see particles flying around it. Now, so the time around you would accelerate slowly, and you would actually not feel any different. You would not feel any spaghettification, you would not feel even a headache probably. You would just feel normal. Nothing would really change for you. And you can see the time has actually accelerated. We get to see the stars moving around us really, really fast. And you can kind of see them in the background as well as their light bends around us. And basically the time would increase. It would accelerate even more. It would accelerate even more. Unfortunately, Space Engine doesn't demonstrate the other star motion, and I'm going to use Universe Sandbox 2 for that, just to give you an even better impression of what happens when you enter the black hole. But basically, at some point, right before you cross the event horizon, the time will move so fast that you will see everything moving in fast forward. Everyone you have known would already have been dead a long time, and the entire galaxy would start changing shapes and possibly get absorbed by the black hole, or possibly would collapse into some other galaxy. And at some point you'll cross the event horizon and you get to see the entire universe in front of you just end. You would literally see the end of the universe and would enter the black hole. Now, the reason I wanted to actually show you Universe Sandbox 2 as well is because of this really cool simulation called Supernova in a Galaxy. So if I were to start this is what you would see. It would be something like 5,000 years per second. You would see a supernova right there, and then it would actually dissipate, and that's it. If you were to accelerate this, obviously you would see every single particle move as well, but I wanted to actually show this to you because it allows me to basically give you an idea of how time around you accelerates. So I'm going to restart this again, start paused, and here we go. We're going to basically go into the central supermassive black hole that's very similar in size to our black hole in the center of the Milky Way. And here it is. So this is that black hole that is in that particular region. Now, just to give you a sense of time, I'm also going to place a few stars around it that move slightly, basically at different locations around it, with possibly different orbital speeds as well. So there's one going to be here, there's one going to be here, let's place the sun in here as well. So each of these stars will have different orbital velocity, and they'll basically give you a better sense and better understanding of time. Alright, so time has started, so now we are basically approaching a black hole. We're starting to experience a little bit of time dilation, and as we get closer and closer, the time dilation increases. Now, if you were to look around now, you would obviously not see any difference. Everything is still kind of frozen in time, but as you get closer and closer to that event horizon, your time dilation increases as well. Your time on your spaceship, or on my spaceship in this case, doesn't really change, but to me the rest of the universe changes. It starts moving a little bit faster. If I were to actually try to find one of those stars now, I would now be even able to see them move across the galaxy. They would actually start moving around me, and as I move closer to the black hole, that motion would actually accelerate. So if I were to look at them again, they would move even faster. and faster and faster and faster. Now, this whole event would not take very long. This would only be maybe under a minute, possibly even 30 seconds. But if I will look really, really, really close, and if I actually am fast enough at seeing things, I would be able to see the entire galaxy around me moving faster and faster and faster. And so if I were to actually look back now and try to find that supernova, I would realize that it's over there, and it's actually increasing in actual size as well. And there comes one of the first stars. So the stars around me move faster, the supernova expands faster. I would start seeing various stars disappearing and new stars appearing, and basically the entire galaxy around me would become fast forwarded. It would actually move a lot faster than before, and you can see all of these particles that represent stars move around me as I'm approaching the event horizon. And as I get closer to it, things will get even faster and faster and more fast. And essentially, this is what you would experience the closer you got to the event horizon. As I'm about to enter it, as I'm about to enter this event horizon, the entire universe spins around me super fast. And not just the galaxy, the entire universe. And my computer unfortunately cannot handle it, but this is essentially what you would experience right before hitting this magical spot of event horizon. And as soon as you cross the event horizon, things get even more interesting. We actually still are not completely certain what exactly goes on there, but what we understand about the physics and the effects is that once you enter the event horizon, you're basically only facing one direction, right into the center of the black hole, the singularity. Even if you try to turn, you'll still be facing the center. Even if you try to move back, you'll still be facing the center. And right in front of you, you'll literally see everything, every historical event that has occurred and entered this black hole from the creation of the black hole. So basically, all of these events that come into the black hole, they will be right in front of you. You'll see the past, you'll see your birth, you'll see your death. Well, not your death, because you are in the black hole, but you'll see absolutely everything in the future and in the past right in front of you. And what's even more interesting is that as soon as you cross the black hole event horizon, as soon as you cross it, the universe behind you ends. You'll literally reach the end of time. You will not be able to go back because there will be nothing to go back to. You will have literally crossed into a completely new reality, another universe maybe, or possibly something completely different. And since time really can only go forward, or naturally only flows forward, what happens after the event horizon is even more extreme. So time and space switch roles. So space no longer is as important, but time is, and time drags you toward the singularity. It actually drags you and pulls you toward the center, which is of course the singularity, where the entire space is just wrapped around you. Now, we still don't really know what happens at the center, and we'll probably never really know because it's something that is impossible to define. But what is interesting is that crossing the event horizon means there's only one way for you, and that's of course toward the singularity. The infinitely small, but at the same time infinitely massive point in space. Now, another way of explaining all of this is, of course, using the infamous Niagara Falls analogy. So imagine you're on a boat and you're moving toward the Niagara Falls. And this is Niagara Falls, of course, represents the event horizon. So if you're still in the water, you can kind of paddle away from the actual Niagara Falls and you can kind of try to not fall, right? But as soon as you cross the event horizon, that's as if you were just over the edge of Niagara Falls. And essentially, as soon as you cross that edge, there's no other way but down toward the ground. And that's essentially you crossing the event horizon and approaching the singularity, which would be, of course, the ground. And whether you die in there or whether you actually live is a question we'll probably never answer as well, but chances are something happens to you and maybe something does occur. But I think to me what's really, really incredible is that once you cross the event horizon, you'll actually be able to see absolutely everything. The entire future, the entire past is going to be right in front of you. You'll be able to essentially explore or possibly go crazy from exploring all of these events that are right there. And the reason for this is because what is happening here is that this is called event horizon for a reason. From our perspective, which I'm going to explain to you in a second, nothing really ever reaches this event horizon. But from a perspective of a person, Anton in this case, who actually crosses the event, he will get to witness everything, every event that has ever reached this black hole at the same time as he is progressing toward the singularity. But I think to explain this a little bit more, I need to actually take the other perspective, the perspective of Anton's sister, Antonia, who stayed at that star and has never actually been adventurous enough to try to reach the black hole. So what happens to Antonia? What does she actually see? And that's actually something completely different. This is yet another mystery of the black holes that will take us quite a while to explain. So let's just say Antonia is orbiting around the same black hole, but Antonia is actually on a planet and just wants to see how her brother Anton does. And so she's right here on this imaginary planet of Mars that is orbiting around the same black hole, but she counts her time differently. She counts her time in seconds per second, so her time basically never really changes. And what Antonia is going to be watching from Mars is her brother Anton taking off on one of the moons of Mars, which is of course Phobos. Now this is Phobos and is going to be moving directly into the black hole at the initial speed of 10 kilometers per second. Now just to demonstrate how the time is going to progress here, we're going to make this Phobos, we're going to make him spin a little bit faster. As a matter of fact, it's going to spin once every second. So here's Phobos flying toward the black hole and it's spinning once every second. Anton is somewhere in the middle trying to hold on and not to fly away from Phobos. Unfortunately, it's kind of dark and black, but that's okay. And so what she's going to be seeing from Mars, from her observational point right there, is this really fastly spinning object moving toward the black hole. So we're going to accelerate time just a little bit, and remember, this is still regular time, regular speed. We're going to accelerate just so it gets closer to the black hole. And as it gets closer and closer to the black hole, its velocity will start increasing as well. And what's going to happen to it is really interesting. As Anton approaches the black hole closer and closer, and also as his speed accelerates toward the speed of light, what she would actually start seeing is Anton getting darker and darker, redder and redder, and this is something called redshift. But at the same time, she would actually start seeing him move a lot slower. So this is why I actually decided to introduce the rotational speed here, because I can show you that things for her, for Antonia, would look like Anton is actually moving in slow motion now. And as he got closer to the black hole, he would start moving even slower and slower and slower. At some point where he gets closer to the event horizon, not only would he be very red and very dark, but he would also start moving at half the speed. Then he would get even darker and slower, and darker and slower, and darker and slower. So at some point the speed of Anton would actually slow down. It would look like, if this was a smaller black hole, it would look like he would actually be stretched and pulled. And right before the event horizon, it would actually look like he totally and completely froze in time and disappeared, because what would happen is that he would actually get so stretched and so redshifted that no more radiation, no more any kind of information would actually reach Antonia from the event horizon, and it would basically look like he just froze right above the event horizon and froze in time. But the interesting thing is that that's all she would see. She would see a frozen Phobos, just frozen in time, that is being bombarded by all kinds of particles orbiting around or moving around black hole, or all kinds of Hawking radiation just bombarding this poor Phobos that's frozen in time. And this entire object would basically just burn in a very interesting and very painful looking death. So for Antonia, Anton would most likely just disappear into nothingness, never to return. And not only would it actually look that way, but that's actually exactly what happened. From her perspective, Anton has now frozen in time and has basically been kind of slowly roasted by Hawking radiation, by all kinds of high energy particles that actually do move around the event horizon here in this vicinity. And essentially for her brother would be, or her twin brother would be actually gone. But for him, she would be gone. And this is where things get really interesting and really tricky. So for Antonia, her brother is frozen right above the black hole and is slowly removed from existence by the things right above the event horizon. But at the same time, he has become invisible and is no longer detectable for her, because all of his waves and all of his radiation that's emitted from his body has actually now been redshifted into infinitely long rays of radiation. Whereas for Anton, who actually entered the black hole, his sister is dead. She's died of old age, waiting for him to return, and the entire universe is also dead as well. And this is where things get really complicated, because how can two events happen? How can things actually exist in two completely different realities? And I think the word here is reality. So the actual frame is really important. This is the so-called black hole information paradox, where no, you're not really a clone, you're not actually, there's no two copies of you. And yes, you are in two places at once, but because in Antonia's reality, the story ended with Anton being right above the horizon. In her world, her universe, this is what happens, and this is the truth. But in Anton's reality, where he actually entered the black hole, his other reality ended. Antonia disappeared and he entered a completely new universe, completely new reality where things don't really obey the same physics, but at the same time, he actually is in a completely different world now. And in his new world, he can actually see the entire universe from the beginning to the end, but he's also required to move into one direction, the infinity of singularity right in the middle of the black hole. What happens then? We don't really know, but essentially he is still alive in his frame of reality, but not in his sister's frame of reality. But anyway, that's kind of what I wanted to leave you with, just to think about it, and in the next one of the future videos at least, we're going to actually explore this in more detail as I find more simulations and more video games that allow me to explore this visually. So let's actually see Phobos entering the black hole, and let's see what happens to Phobos as it enters the black hole. But just think about it, how crazy is that? You can actually have two frames of reality, and this is actually what general relativity tells us, that it's always about where you are, not where everyone else is. So your frame is your world, it's your universe. And if your universe moves into the black hole, that's where it's going to stay. If your universe is on Mars orbiting a black hole, that's where it's going to stay. And this is where things get a little bit tricky. Anyway, hopefully you enjoyed this video, and if you did, don't forget to subscribe and don't forget to share this and like this video as well. Also check out some of the other Universe Sandbox 2 videos that I've posted previously, and most importantly, support the developers. Support the developers of Universe Sandbox, purchase the game if you still haven't, or go and download and possibly donate to the developer of Space Engine, because it's absolutely free, it's awesome, and he basically just asks for optional donations. And in the next video, I'm going to actually demonstrate to you what happens when you move at the speed of light, because I just found an amazing simulation that allows you to see that. And to show you exactly what we've detected and how it's actually been found, I'm going to be using Universe Sandbox 2 to actually recreate the solar system where this black hole is located, because there is actually still a star in the vicinity, and that is why we were able to kind of see what's happening. So let's actually start a completely new simulation here, and we're going to place a black hole in the middle. And here you go. So this is a black hole called V404 Cygni. It's about 9 masses of Sun, so it's a relatively small black hole in terms of its size, in terms of its mass, compared to obviously other supergiants. Now let's see what's happening here. So we know that there is a black hole in the vicinity here, but we also know that it has a companion star, and its star is a little bit smaller than the Sun. Now, so if this is the black hole right here in the middle, the Sun is actually going to be placed a lot farther away. As you can see, the Sun is huge compared to this black hole. So we're going to place it at around a million kilometers, or actually 10 million kilometers away from the black hole. So there you go. So it's going to be orbiting the black hole. And this is actually what's really happening in this particular system. And as it starts orbiting the black hole, because it's actually relatively close, a lot of its gas gets sort of streamed away from the black hole. It's basically, it gets sucked off into the black hole and creates this really beautiful vortex. So to create this vortex visually, we're going to go into the rings here. We're going to add rings to this black hole. So it's going to be anywhere between 9,000 kilometers and about 10 million kilometers in distance. Now this is what would happen if you just added regular rings, so this is what it is going to look like. It sort of creates this accretion disk around this black hole, but we want this to be a little bit different. Let's actually use slightly different color. I'm going to use silicates here, and we're going to place a spiral that is going to be exponential in the way it grows. And here you go. So this is what I was kind of looking for. There we go. Now the only problem is that it doesn't actually start from the star, but as you can see, the star sort of sucked in this particular vortex. So we can actually add a few more. So let's add a few more, and I'm going to also increase some revolutions here because I want to have different types of vertices. And so what you can kind of see here is, if you were to sort of look from the angle where it's more visible, a lot of the material basically gets sucked out of the star and sort of slowly gets to be sucked inside of this black hole. And this is essentially what creates this accretion disk around this black hole. Now, as this accretion disk is created and as it starts sort of orbiting the black hole faster and faster, the energy released by this accretion disk starts to basically be increased dramatically, and it reaches the point where the entire matter here starts to glow because of the heat. And as it starts glowing, as it essentially acquires this glow, it starts emitting different types of energy. Now, obviously, it emits a lot of X-ray radiation closer to the black hole, and this is actually what we see quite a lot. We've been able to detect various X-ray emissions from the region of black hole, because at some point this really highly energized material gets sort of ejected by the black hole, usually in two directions, directly up and directly down. And we've seen this many times, and this is actually how the idea of a quasar is born as well. But this time around, we didn't just see the X-rays, we've actually been able to see the optical waves, in other words, just regular color. So at some point, as this material starts spinning around the black hole, and as it sort of starts glowing, it started to emit actual visual glow, and this is actually what it kind of looks like. You can kind of see it right here. And so essentially, we've finally been able to see a black hole. So it's not as black as you may actually think, because we can sort of see it. Now let's see if we can add some more rings here just to make the spiral more pronounced. And we're also going to create different colors of this spiral here. And okay, I think I've added a little bit too much, but there you go. This is kind of what it actually looks like in a binary system where there's a black hole and another star next to it. So a lot of the material basically gets sucked off from the sun and goes inside the black hole until the sun no longer exists, and at this point black hole just stays and becomes a lonely object. Now I've done this a few times, and it actually looks different every single time. I do recommend you try this yourself if you have Universe Cinebox 2, and if you don't, it's probably a good time to buy it because it's a pretty awesome game. But I'll show you another simulation I've created recently that had a slightly larger sun and slightly larger black hole, but a completely different looking sort of binary system. So here we have a very large amount of accretion disk next to the black hole that's orbiting around it really fast, and this is actually where the glow would be created. And then you have this sort of a spiral going out into the star. Basically, this is the material that gets ejected from the star because of the gravity and slowly sort of makes its way toward the center of the black hole. So this is another pretty cool simulation of what accretion disk might look like if you were to come closer to the black hole. Obviously, there would be a lot more material, but my computer unfortunately cannot handle this much. This is already a sort of a limit of what we can do here. And you'll notice that once in a while there will be these particles that get ejected really fast into the outer space here. Now, unfortunately, this is not exactly how it works. We know that for some unknown reason, black holes eject things only up and down, or at least that's what we believe. And there is no mathematical model for how and why they do that just yet, but we know that this is how it usually happens. So it's very unlikely that things would actually fly out this way, or that it's possible, but it's more likely that they'll go up and down, mostly probably because of the spin and the way the space is bent around the black hole. Anyway, so that's all I wanted to talk about in this video, and I just wanted to recreate this binary system where we have a black hole and a star, and just to give you a visual representation of what this might look like. And what's really interesting about this particular system called V404 Stignii is that it's actually been quiet for many years. We didn't really see anything from it, and it's actually also the closest black hole to us. It's only about 8,000 light years away from the sun, which is not as close as you think, but it's the closest black hole that we actually know of. And after about 26 years of this system being completely dormant and not really doing anything, it suddenly started to have these outbursts of X-rays, which basically indicated that there was material that was being dragged inside the black hole, and it sort of got ejected at ridiculously high speeds and produced a lot of energy. At some point during these 26 years, this was actually also the brightest object we could detect in the universe because of the X-rays it was emitting. But it was not until very recently, specifically for me, only last week, late March of 2016, that we've finally seen a visual representation of this black hole. And according to the scientists, if you have a moderately powerful telescope, you might even actually be able to see it yourself. If you're to look in the vicinity of this black hole, there is actually a bit of a flicker that you might be able to detect. This is a black hole that has an amazing accretion disk orbiting around it. Now, this is actually 1 second per second, so I have to slow down time just to show you what it really looks like. So it's a very, very fastly spinning black hole that has a huge accretion disk around it. This black hole is not particularly massive, so actually if I were that close to it, I would already have been killed miserably through spaghettification, about which I talked about in the previous video. But here, you are actually now able to approach the black hole and sort of see this really cool effect, very similar to what we see in the Interstellar, that sort of had a very similar supermassive black hole that had an accretion disk. We'll talk more about accretion disks a little bit later in one of the future videos, because today we're just going to answer a few questions and clarify a few of the confusing things that have been raised in my previous video. So first of all, let's actually move away from this black hole for a second. We're going to come back to it in a second because I have it saved, and we're going to go to the previous black hole that I explored when just looking around new galaxies that have been created in this beta version of Space Engine. So this black hole right here is actually part of the binary system and is not a very massive black hole. It doesn't actually have an accretion disk. It's just an empty black hole all by itself. It's actually kind of hard to find as well, so I do need to use this right here to try to point out where it is. All right, there it is. So let's move closer to it. We're going to go to Object, and I'm going to show you one of the really cool additions that have been added. And you may have already noticed it, so let's just remove the orbits for a second, just so you can see it better. What has been added, and this is actually something that I'm going to be exploring in more detail in the next video as well, but basically we now have blue shift in the game. As I'm approaching the black hole, the space-time warps around me, or basically the entire space-time around the black hole starts warping more and more, and the light behind the black hole starts being blue shifted, and you can see it's becoming more and more blue because it's being sort of, I guess you could say, launched at me, or that's not really the right term, but it moves toward me with a lot more energy than before, and because of that, it's being blue shifted and everything around me becomes very, very blue. Now, first, what I wanted to really show you in this particular simulation is what really happens visually when you enter a black hole. And this is, I'm really happy they finally added this to the game because it wasn't really possible before. But so what happens when you enter black hole? Like I mentioned before, first of all, obviously the time around you will start speeding up, so everything will be moving a lot faster. You'll start noticing stars whizzing by. The entire galaxy will start spinning faster and faster. Also, you'll obviously start seeing a lot more blue shift. Things will even become more ultraviolet, more X-ray-y, and a lot of these waves will eventually become invisible because they'll become ultraviolet. So right before I enter the event horizon, if I look around here, a lot of things are very, very, very blue because they're very blue shifted. Now, and behind me, that's what it looks like as well. Now, as I move closer and closer to event horizon, I'm going to look into my side window now. This is what's going to happen. At some point, half of my view is going to be event horizon, the blackness, and half of it is going to be this blue shifted universe that is moving really fast around me. It's sort of fast forward. There it is. You could actually see the star whizzing by. It's fast forwarded because I am now in such a tremendously warped space that everything around me is not experiencing as much time dilation as I am right now. And so I am essentially now a time traveler, which is actually a pretty cool concept when you think about it. And I think this brings me to one of my first questions here. And the first question is from Rage Bogey, I think. And the question is, why does time speed up? And also, how come I don't actually feel it? Well, so why it speeds up is a very interesting question. And that also relates to the idea of space-time. So I'm going to kind of tease you a little bit and exit the black hole for a second. I'll show you what the inside looks like later. And so why does time speed up? Well, because everything here, everything in the universe, everything around you, everything around us is essentially space-time. It's not space, it's not time, it's space-time. It's sort of like the same two faces of, different two faces of the same coin. So think of a coin that has two different faces, so that's space-time. Actually, this idea is not from Einstein, it's from his mathematics professor by the name of Hermann Minkowski, who originally, something like in really early 1900s or possibly late 1800s, came up with this four-dimensional idea of space-time. And so you really have to think about space-time as a kind of a continuous one thing. It's not two different things. Time is not separate from space, and space is not separate from time. They're basically just one long, voluminous, huge thing. A thing that can actually be manipulated, it can be stretched, it can be condensed. And because it can be stretched and condensed, obviously one thing will influence the other. And so when you're actually next to a very massive object, which obviously warps space around it, the time will also be influenced. And so here you have to really think about perspective. So even though from one perspective, time may actually seem like it's moving at this fast pace, if you were to go into a different perspective, time would now, because there's no more mass influence in it, time would now move a lot slower. Where's that star? I don't even know where it is anymore. It flew away from me. There it is. So time in a different perspective, even though you look in the same object, now actually moves differently because you're really looking at all of this from a completely different view now with a completely different space-time parameters. And so this is kind of similar to the idea of just looking at objects in space. So if you were to look at a star, if this star is, let's just say, how far away is this? It says 15 light years away. What I see from my perspective right now is actually an object that emitted light 15.5 light years ago, and I'm actually seeing the light that is 15.6 years old. I don't see the real light that this particular star emitted. So this light is already 15-something years out of date, and we can therefore never really know what the universe is like at any instant. Because universe doesn't just exist in space, it actually exists in space-time. So both space and time are related. For me to see what the star is really like, I have to approach it, and as I approach it, time will pass. And so obviously to cover this space, I will have to spend time. So once again, space-time is related, and what I'm seeing from my perspective is very different from the perspective of that particular star. And so in today's modern science and in physics, we don't really think of time as passing or flowing. Time doesn't really behave in such a manner. As a matter of fact, the way we think about time is that it's essentially just there. The past, the future, and the present are basically laid out already in this so-called space-time. It's already there, and essentially it can be explored in both directions. Now, if this is all confusing, you are not alone. Don't worry that if you didn't really understand what any of this means, but think of really this whole space-time thing as mass and energy. Today we know that mass can create energy. When you explode something, when you explode a nuclear bomb, you create energy, and energy can actually create mass. Energy, if you create a lot of energy, it will eventually turn into mass. And because of this energy-mass connection, you can kind of think of space-time connection as well. I think it's a pretty good analogy. So think about it. If mass can become energy and they're basically just one thing, why can't space and time be the same one thing? Anyway, moving on. Let's go to the next question. And the next question is from a person by the name of Ahmed Sao. And now, this person actually asked two questions, but I want to answer the second one because I'm going to answer the spaghettification question in the future. But this question here, how can we see the future near a supermassive black hole? So this is how. As you approach the supermassive black hole, if you actually are right here, it's not just that you see the future, it's that you actually see the entire universe fast forwarding, and as you pass into the black hole, I'm stuck inside of it now. As you pass inside the black hole, you're essentially are seeing the end of the universe. You're seeing the future and the end. It's not that it's the future, it's just the present for you has been accelerated into infinity. So what you're really seeing is the time outside, your time is essentially being fast-forwarded into infinity. So for people outside of this perspective, for these people, it may seem like the future, but for you, it's not the future at all. It's actually your present. It's being accelerated and moves really fast. And a very similar question is from a person by the name of Louis Bloch, and he asked that if you go closer to the black hole and time gets faster, doesn't that mean that you just time traveled? Well, it kind of does mean that you time traveled, especially if you can actually approach the event horizon and somehow then move away from it. You will actually find yourself in the future. I mean, it will be your future. Everyone that you know has already technically died, and Earth is very likely have been destroyed as well. So it is future, but at the same time, it is once again your present, because it's always all about your perspective. And another really interesting question was from a person named Hi Bye, or is it Hi Bye? Anyway, he actually asked quite a few questions, or possibly she, and one of the questions was this. So, is it true that the gravity also slows down time, not just speed? And the answer is yes, it's true, and this is why the time would slow down if you come close to the black hole. But what I wanted to talk about is not actually a black hole, but the real phenomenon that exists on Earth, and that is very, very important for us when we're using things like GPS. And for this particular simulation, I'm actually going to try to come closer to this planet so you can kind of visualize what's going on here. We're going to slow down time a little bit because it's spinning a little bit too fast. I believe this is some sort of a cool ice giant. So on our planet, if you stand on the surface of our planet, and I don't know if I can land the surface here. Yeah, look at that, we can. If I am on the surface of this gas giant, the time for me is actually moving a little bit slower than the time for an astronaut or for a satellite that is above me. Because I'm closer to the gravity pool of our planet Earth, and or in this case, this particular cool ice giant, that's actually what it's called, cool ice giant, the time for me, because I'm closer to the pool, here is actually slower than it would be here if I was in orbit around it. And for this particular reason, our GPS satellites have to actually actively calculate the gravitational effects and the time dilation effects, and have to actually add like something like a few milliseconds every year or so, because since they're actually above us, they don't experience as much time dilation. And for this reason, let's just actually imagine this for a second. So let's imagine you have a twin brother or twin sister, and you decide to stay on this ice giant inside this really cool looking hurricane. So you're basically closer to the surface of the planet, and your brother or sister is somewhere outside orbiting around this planet on some sort of a new space station. After a few years, your brother or sister comes back to the planet, and you'll realize that he or she is actually a few milliseconds older than you, because they've experienced time dilation a little bit different from you. So this is kind of how it works, and this is why our GPS systems have to be always constantly adjusted for this type of a dilation, otherwise they will not be very accurate. Alright, so let's go back to that black hole, and I'm going to answer one more question that's actually, I guess many of you have been asking and kind of wanted to know what the answer to that is, so we're going to go back here. And the question is this comes from a person by the name of Advanced Prime. What is the theory, or what is my theory of what happens when you enter the black hole? Now, so this is actually what I really wanted to show you in this video. This is the new addition to this simulation, and this is the visual representation of what happens when you enter a black hole, and then I'm going to talk about the theory of what might happen afterwards. We're going to be entering this event horizon. We're going to be looking into our side windows, because in front of us is just blackness. As you pass by the event horizon, at some point, if you were to look back, this is what you would see. The entire universe, everything in the universe would start slowly be turned into this, a tiny circle. This is not just what you see behind you, this is everything. Everything would become a circle, it would accelerate in time and would accelerate into infinity and then disappear forever. Forever and ever. You would see nothing afterwards. That's it. You're in complete darkness. You're inside the event horizon. You're inside the black hole. Now, remember how I told you in the previous video that every other event would also be actually seen in this particular moment? And this is what I think would happen. So, because every other event that has crossed the event horizon would now be in front of you, or possibly behind you, but very likely to be in front of you, because there's really only one direction now. There's only this center, which is towards singularity. You would now be able to essentially see, and I guess maybe even feel, everything at the same time. All of these events that cross the event horizon at some point would now be right in front of you. Now, this might not last very long, and depending on the size of the black hole, it might actually last only a few seconds, because as you approach the singularity, theoretically what should happen is that you should finally be spaghettified, you should finally reach your destruction and be completely destroyed. But it's very likely that you might also end up in a completely different universe, in a completely different place. And this is actually what I think would happen, because you're now in a completely new environment where you have, not just environment, completely new universe that has all of these events that crossed with you that are actually not present in the previous universe anymore. So that universe that we've left, it's gone forever. You cannot return to it anymore. You're now in a new universe and have all of these events that crossed into this universe with you. And so now you might actually have a completely new life in a completely new universe. And that's, I guess, more of a positive thinking. But anyway, we can actually, at least in this game, fly through this black hole, and we can actually possibly even come out on the other side. I missed the other side. There you go. We are now going to be coming out on a completely different side of this black hole. And this is what you experience if you were to kind of be able to come out of the black hole. But this is not even theoretically possible. It's impossible to come out of the black hole or the event horizon, at least without some sort of theoretical concept that we haven't really come up with yet. So technically, once you go in, that's it. And what happens afterwards is anyone's guess. Anyway, so before I finish this video, I actually just wanted to answer one more question, because it's kind of, I think it was a pretty good question. It's actually one of the more unusual questions that made me think. And the question is this, and this is from a person by the name of Kawaii Ninja. What happens if the solar system is near all the star clusters that's around the black hole? Will the sky be very bright? And that's an excellent question, because it absolutely is true. It will become very, very bright. I'm going to show you using the new addition to the game, which is obviously the actual central black hole in our galaxy. If I were to go to the supermassive black hole in the center of our galaxy, this is what it will look like. And let's just say you're orbiting somewhere here, or basically this is your home star. This is where your home planet is. If you were to look into the sky from this home planet, the sky would be ridiculously bright, much, much brighter than our sky, because the center of the the center of the galaxy, near the central black hole, has so many more stars than the part of the galaxy where we are. And because you're so close to the black hole, there's actually a lot more stars orbiting around it, so you would actually see something like this. And this is obviously accelerated, but you would see a lot of these stars just kind of orbiting around you faster than usual. As a matter of fact, every year or so, your actual view of the sky would change completely. So keeping track of constellations and keeping track of actual stars would be relatively challenging, because there would be just a lot of motion, a lot of really awesome bright skies and bright lights everywhere. And obviously, you would also have this really, really interesting, really scary looking black hole in the sky as well, and you would really only see the accretion disk and possibly any kind of effects from collisions with the black hole, because whenever a collision with the black hole occurs, it does release a lot of energy. But depending on how far away your actual home planet is from this black hole, you may just see a kind of a bright light right there. So it's very difficult to see it. We're gonna have to come closer just so you can see it. But the accretion disk here is essentially what creates this type of a look. So it does kind of look like a star, but it's not really a star. It's really a supermassive black hole with a lot of energy and a lot of accretion disk particles orbiting around it. And anyway, let's go back to Sagittarius A. This is our central supermassive black hole. It's finally been edited to actually represent what it really looks like, and it has its actual realistic mass of 4.3 million masses of sun. And this is the stars orbiting around it as well. These are the stars I talked about in one of the previous videos. Anyway, hopefully I kind of helped explain some of these questions you guys had, and hopefully I made this a little bit more clear. If I made this more confusing, please post more questions so I can answer them as well. And I guess the takeaway message from this entire series on black holes, and also this video in particular, is that you have to just remember that, let's actually slow down time before I explain this. You have to remember that there is something called cosmological principle, and this principle refers to a simple idea. The center of the universe is actually everywhere. Scientifically, you are the center of the universe, but then again, so am I. So is this black hole. So it's really all about the point and the perspective from which you're observing the universe. So if I'm observing the universe from the perspective of very close to the black hole, my entire universe is different from yours, and my time, my space, and everything in time-space for me flows very differently from you, where you are. And this is the really important concept in physics and in astrophysics as well, because this is essentially how the entire universe works. And so whenever you're trying to think about the universe, think about any kind of stars or any kind of black holes out there, you really have to always think about the perspective from which you're actually thinking about them. And so this cosmological principle is the reason why universe is actually so counterintuitive and so complicated. Anyway, I hope you enjoyed this video, and I hope I answered some of your questions that you had in previous black hole videos. And thank you so much again for helping me reach 15,000 subscribers. I love you guys so much. Thank you for everything. Feel free to post more questions. They will definitely be answered. And if you want to contact me, don't forget there's always the Facebook page that I usually check very often and always answer every question there as well. Hello wonderful person, this is Anton, and welcome to a video about black holes. Now, I've done these videos before and I've actually talked about black holes previously, and so I decided to actually talk about a very interesting speculation and possibly explain a little bit more to you using a bit of space geometry and a kind of a visual representation of what black holes are all about and what might be actually happening inside of them. So we're going to be using a combination of Explain Everything, which is an app I use for an iPad, and a beautiful black hole video that you see in the background. So let's just start with a little bit of mathematics. And here I'm just going to kind of just draw something you might be familiar with. This is called a space plane where we basically have 3 dimensions. Now, most of you I think are familiar with this idea. So you have, actually this is not Y, this is Y. X, Y, and Z direction. And this is what our space kind of looks like. This is how our space is represented. And this is where we are all located. So I can actually draw a little person here in 3D space. This is what we would refer to as 3D space. Now, we're going to be talking about space-time. And to talk about space-time, we actually need to possibly get rid of some of these dimensions just to make it a little bit more visually comprehensible. So let's just try this again. I'm going to go to a new slide here. And this time we're going to change the 3 dimensions into... First we're going to change them into 4 dimensions. So we're going to have a dimension of time as well, because that is what space-time is. Space-time has actually 4 dimensions. And here we're going to start getting rid of the 3 dimensions that we have for space. And this is just to make it a little bit easier. You may have actually seen a picture that looks something like this, where you kind of have an object in 2 dimensions where it bends the space-time. But instead of using 2-dimensional space, I'm actually going to go into 1-dimensional space, because it's a lot easier to imagine things that way. So imagine that this is actually this. So inside of this, there's actually 3 dimensions. And so we have this dimension for space, and then we have this dimension for time. So we have time and we have space. Now, hopefully so far this is pretty easy. Now, the interesting thing about the space-time dimension, or I guess the space-time axis here, is that we can freely move through space. We can basically go anywhere we want in 3 dimensions. But in terms of time, we're always pointing in 1 direction. We're always falling through time in 1 direction. This is essentially how time passes, right? So we're all familiar with the idea of, passage of time, and obviously it's a concept that is difficult to explain, but it's in everyday life. And so why are we even doing this? Well, because when you actually start changing space, when you affect space by putting something massive in the middle, you will actually affect time as well. Now, this is often represented in 2 dimensions, but this is why I decided to get rid of that 2nd dimension, because it will make it a little bit easier. So imagine right here in this space, I put an object right here in the middle, and this is basically, let's just say it's some sort of a planet. It doesn't really look planetary just yet. Let's make it a little bit more planetary looking. And so here is a planet in space. This planet will act on space-time and will create this kind of a bump right here. The bump of space. it will essentially fold space and create a bit of a disruption here, or distortion, I guess you could call it. And so even though right in this area and in this area, time passes normally, this is normal passage of time, right in this bump, it is actually going to pass a little bit differently. It's going to be kind of slower. So, for example, maybe 10 seconds in this area and 10 seconds in this area would actually be only like 9.999. But let's just say this is a massive planet. So let's just say it's going to be 8 seconds here. So the time actually starts passing slower for the person in that particular, on the surface of this planet. So for a little person that is on this planet. So if this person right here and another person right here are actually twins, and if you basically take this twin outside of this planet and let him stay in this area, and then take the other twin and put him on the planet, with time, the green twin is basically going to be younger than the blue twin. And this is something we've observed in real life. This is actually something that we need to be aware of when launching satellites, and also this is something that is or has been proven many times. This is essentially Einstein's theory of relativity. But let me just show you what this actually looks like in terms of realism. So let's just say we're going to need to place the planet here again, because the actual folding of space is a little bit different. So the folding starts from outside of the planet. So here space starts folding as you approach the planet, and it's going to be the highest at the surface of the planet. So right here there's going to be 2 points where the fold is going to be the strongest. This is where the passage of time is the slowest. And it's the same on both sides. But the thing is, in the center of this planet, the gravity is actually, it's basically non-existent, because you get the attraction from all sides, equal attraction from all sides. So here, right in the center, the passage of time is going to be regular. But up to that point, we have this kind of a curve. So this is what a space curve would look like as you approach the planet, and as it essentially is being folded by the gravity or by the mass of this particular planet. And so that's essentially how massive objects affect the space-time. But obviously when it comes to black holes, and here we need to kind of change this a little bit, I'm going to just draw a very massive object first. This is not a black hole, I'll just say this is like a neutron star. A very massive object is going to affect the space even more. So the space here will bend or fold even higher. And then, basically, this is a horrible picture, but you get the idea. Here, the passage of time is actually going to be even more extreme. So on the surface of this neutron star, the time here will actually be very, very, very slow. So here, a regular time of 10 seconds might actually become something like 0.5 seconds. So time will be much, much slower. And as the object becomes more and more massive, so if this is suddenly even more massive, the time will obviously start decreasing as well. So if you were to actually stand on the surface of a neutron star for like, I don't know, 10 seconds of your time, if you were to leave the surface of this neutron star and come to the real world, you would realize that something like thousands and millions of years have passed. But at some point you reach such a high gravity and such high bending or folding of space-time that you create something called a black hole. And this is where things get really, really creepy or scary. The fold becomes so powerful that it just kind of goes into the extreme of space. So there's really nothing here on the bottom. And this is what a black hole would be. So the time here would slow down and slow down and slow down and slow down, slow down, slow down, until it's essentially stopped completely. Now, is it actually stopped? Is it actually going to be stopped completely, or does something else happen here? Well, the speculation that I've heard about, and I kind of sometimes think about as well, is that, well, what if inside a black hole, time actually reverses with space? Let me just explain to you using another picture here. So before we were talking about the three-dimensional space that has 3 directions. So before we were talking about the 3-dimensional space, and with 4-dimensional was basically time. And here we can move freely through 3D space, and we're always falling through time. always falling through time. Now, what we know about black holes is that once you actually reach the black hole, once the space becomes really, really stretched, you actually start falling into a single direction. So, in other words, as you stretch the space-time, as the space-time in one direction becomes stretched, and the other space kind of remains the same, and as the time sort of shortens, which is essentially what happens as you approach the black hole. So these will stretch dramatically, and the time will shorten and start passing slower and slower until you kind of reach event horizon, where the space becomes there's only one direction of space. Let's just say x-axis. You always start pointing into the same direction. All of the other directions disappear. There's nothing else left here. But what happens to time? Well, time does stop, but does it though? It might actually be a very far-fetched speculation, but what I've actually like to think about sometimes is that what if actually they reverse? Because here in the previous example, in this example, we were falling through time and we were able to move through space. But we know that in the black hole, we are falling through space. So what happens to time? Maybe we actually are able to then start moving through it in 3 dimensions of time. Now, that's a trippy idea. Let me just actually redraw this so it makes more sense. But what if, because we're actually falling through this direction of space now, just like we are falling through time right now, we can now, inside the black hole, move through 3 dimensions of time. Now, what are those 3 dimensions of time? What exactly does that mean? Well, this dimension is, it's basically future and past. But these other dimensions of time are the so-called parallel time universes. Basically, we can now move through various multiverses that are actually still speculative, but we're almost certain that they do exist. So maybe, just maybe, if you get inside the black hole, you'll actually be able to move through, essentially, through time, through various multiverses as you're moving through this one direction of space. Now, whether this is actually true and whether this actually makes sense, I don't really know if we'll ever find out, because it's a very, very big speculation. And if you ever reach this black hole, let me just draw it in a different color. If you reach this black hole, there's nothing telling you if you're ever going to come back to tell the truth to everyone else, because maybe, just maybe, the universe will actually end and you'll find yourself in a completely different multiverse somewhere right here with a completely different set of X and Y axes that you're going to be traveling through now. And anyway, so that's basically all I wanted to talk about in this video. It's a very kind of a speculative geometry-based video that I wanted to talk about while using the Space Engine. Hopefully you enjoyed this and hopefully you learned something from it. And if you did, don't forget to subscribe, share this video with your friends, and also possibly like this video and comment about any other ideas that you might have. Thank you so much for watching, guys. I appreciate all your support. I'll see you in the next video. Game you later, and as always, bye-bye.